Welcome back to another live electronics reverse engineering and cat stream. Speaking of the cat, my cat Tuco is always a good way to start things out. Let's see if we can find him. Hey Tuco, where are you at, little dude? Oh, I see him. Hey little dude. Welcome to the internet. Again. Let's announce this stream a little bit. Alright, Tuco. You might notice more of a mess than usual. I'm in the process of transferring the streaming equipment into this rack. So right now I've got this sort of mess of computers. Like, it's not even really obvious how many computers there are in there, given how much of a mess it is. So there's a lot of parts to clean that up. Jarrett responds to my streaming with some screaming, which I guess is a good response. But yeah. Oh, and thanks for posting the link. I was afraid to open that on any computer that was connected to this audio rig because I might set up another infinite loop of audio feedback. So yeah, this will be a stream soon. I might do some of the boring setup ahead of time, but I think I'm going to try to do at least some kind of lo-fi stream this weekend as I get the hardware moved from the previous place into the rack. So that should be nice. I think I have the bits and pieces I need to make that actually work. But today's stream is a continuation on the kind of small projects based around this particular D-Link DCS-933 camera. So this camera first, oh, there's no Twitch links. Oh yeah, yeah. So apparently Twitch links, we discovered autoplay in the chat. So although I have the audio routed slightly differently in this stream than I did yesterday, so at least we won't get a sound feedback loop if that happens, assuming I don't have the chat open on any other computer here. So I think it'll be fine on my end, but it will apparently mean that anyone who's logged into the chat gets another copy of the stream playing that they have to go figure out how to turn off. So that's a little bit annoying. Might be nice to try to fix that in CSS. So previously, this camera appeared in a few other places. Let's see. I don't have it currently in its assembled state, but we can at least take a look at the bits and pieces of this camera right now. So this is the circuit board. The side you're seeing would normally be pointing out toward the front of the camera. So I've taken off this board, which has a switchable infrared filter. It has infrared illuminators and a light sensor with an infrared filter over it. So this is all about the camera's night vision support. It switches between a night vision mode where it's sending out IR light and not filtering that out on the way back in, versus a daytime mode where it filters out the IR and the sun so that it gets more accurate colors. So this board is basically the night vision support plug-in module. And then everything else is on here. There's a camera chip on the front, and on the back side, which I won't turn over quite yet because this is set up for the next step, but on the back side, we were looking at that a lot on earlier streams, and we found this application processor, which was actually a system-on-chip designed for, hey Tuco, a system-on-chip designed for Wi-Fi routers. So it has a Wi-Fi radio, an Ethernet switch, and a processor that's pretty good at running embedded Linux. In this case, it's a 400 megahertz MIPS processor. A little weird. People still use MIPS in Wi-Fi routers, but it's not nearly as common as ARM these days. So we saw this in a few previous streams. First, there was a stream where this we were just interested in getting access to the serial debug port. So there's a serial console on here, which is actually just going to boot you into a root shell. That is actually this tiny little connector here, which we could have found the right connector and populated that unpopulated spot on the circuit board, built a wiring harness to match that connector, but it was easier for prototyping purposes just to solder some tiny magnet wires to that. So here we've just got a little magnet wire harness soldered to that connector, broken out to a little UART 3.3 volt serial adapter that connects to USB. Hey Tuco. He's actually pretty good at not disturbing things when he walks around my desk. Tuco, you're a very careful cat. Cat butt. Anyway, so that's connected to this little blue USB to serial dongle, which is a doodad you can pick up from Adafruit. This one uses the Prolific chipset. I've also got this Saleae Logic 16, which we'll be using a little bit later. This is the model. It's not the one that you can currently find. This is the one that you can actually find a lot of really cheap clones online that work really well with SIGROC. So I'd like to do a stream in the future where I use these with SIGROC. But right now, just to keep things a little bit simpler, and since I'm not familiar with that software yet, I'm going to use the Saleae software. But the important thing about this logic analyzer is that I can run up to 100 megahertz. So in this particular test, I'll need to be capturing 3 channels at 100 megahertz. So this one will just barely handle that. I'm not quite sure how to pronounce your username, but Amkelet says that that's a very photogenic cat, or that's a photogenic cat. I added the very because that's my own bias. But yeah, I agree, obviously. Speaking of, Cat's already inspecting those new server cases that arrived today. That's part of my strategy for racking all this stuff. Len says he's probably careful because he hurt his paws on random tools and ICs. I don't think so, not that I noticed anyways, but yeah, it's possible he learned the hard way, but I think I would notice if he was like bleeding or anything. He did have one problem with an ingrown nail in his paw that I had to take care of a while ago, and that was certainly something I noticed. But yeah, the cats are pretty good at navigating like that. So, anyway, I was talking about the history of this device just to give a little bit of context. This is I think it's marketed as a cloud-connected camera, basically. So it comes in a case. I'm about to try to take this up to the camera without dumping all the screws out. These are the screws that held the little IR circuit board on. I kind of want to put these in another little plastic bin. Go. Bins so fresh they still have the brim on them. Let's keep these separate. It's a little big for something like this, but I think I'm going to put this whole case in there too. So I'm not going to snap this all the way together because it's a little annoying to take apart, but if you ignore the hole I cut in it and the additional wiring there, this is basically what the product looks like. It's a little D-Link thing. It has Ethernet and Wi-Fi. That would be the Ethernet. That would be 5-volt power. And it's basically a Wi-Fi router and a webcam on the same circuit board. It runs embedded Linux. This one's already had a lot of sort of open source attention paid to it also. Like, apparently there's OpenWRT support for this. And at some point, D-Link even released some significant portion, perhaps even all the firmware is open source, but I haven't really looked into that personally. So as far as this stream, this camera first appeared when we were just opening up a whole bunch of them to get access to the serial debug console. So this is what will show the bootloader and the Linux kernel booting up, and then after boot, this actually drops you into a root shell where you can interact with mostly BusyBox and a few of the applications that come specifically on this camera. And then we took a look on the last stream at just the layout of the circuit board and what kind of onboard buses we might see in between chips. And so on this board, we didn't really see a whole lot besides the, well, so really it boiled down to, maybe this is worth breaking out a quick DaveCAD session. I can draw up the layout we discovered last time for this board. So I was mentioning before that when I look at the connections between chips on a board, I really like thinking about it in terms of the trust relationships that are implied between various pieces of hardware. Because that's where things get really interesting for reverse engineering. If you have this one piece of hardware that, in order to get its job done, needs to pass data back and forth to another, or it's grabbing a program or a key from another piece of hardware, that's where you can really get some interesting information just by looking at the connections between hardware. And you can even cause what might be, in some contexts, be a privilege escalation by manipulating signals that go between chips. For example, if you have, let's see, can I come up with like a real world example here? This is something that you might have heard of in the kind of like video game hacking community. People would make these mod chips for some consoles that worked by getting in between the signals that went between the console motherboard and the DVD chip, because the optical drive is just another microcontroller. So in this case, there's going to be some kind of, wow, everything's shaking, and I had that moment of, is this an earthquake? No, it's the neighbor using their exercise equipment. Where was I saying that? Yeah, so looking at the trust relationships between components gets interesting when you have these kind of really complex systems that have networks of microcontrollers that are all talking to each other. So I think this was the case on the Nintendo GameCube, where you had a kind of main processor, you had a, you had an additional processor for security, but that was on another big complicated system on chip. But there was this bus that you could get in between these two processors, where you had a couple of system-on-chip processors on the main board. You had another system-on-chip processor on the optical drive, and that one was actually responsible for a decent quantity of the security of loading a disk. So for this mod chip, you could actually break the security model that was implied to the original processor by just kind of forging responses from that would have been that second optical drive processor. So you can do interesting investigations like that to get access to data you wouldn't otherwise have access to. In that case, they were doing it for piracy, but like I'm often interested in doing stuff like that for just getting access to more of the system, just for seeing what's going on, for evaluating it. In this case, when we looked at the buses between kind of onboard components, wow, I just got this new mat and it's actually still kind of sticky. It's like, let's see if we can get a better view of our CAD window. So we have a couple of chips here. We have this OV780, which is the camera processor, and it's got a lot of stuff inside, including an MCU. We have another processor over here, which is I'm actually going to look at the number on this one. RT3352. And this has our main MIPS core at 400 megahertz. And we already found out the connection between these two is USB. And this is USB 2 at 480 megabits per second. This is actually connected to the camera chip itself over some kind of fairly wide parallel bus. So this is going to have hardware that's processing the camera data, storing it in memory somehow. And if you were building a USB webcam, you would really just be taking the stuff on the right side of this dotted line, putting it on a board, putting it in a box, and selling it, and that's pretty much it. So this has its own firmware. That firmware actually gets loaded over USB from this processor. Then this processor is attached to some RAM. I'm just going to label that DRAM. That's just a parallel bus. That's potentially pretty interesting, but very hard to sniff because it's just a lot of wires and a lot of megahertz. Then over here we have this SPI flash. And this is 8 megabytes, or 64 megabits. And this is just SPI. So aside from some power management components and some, I guess, some GPIOs that are running the peripherals here, I haven't traced out where the control, for example, like for the night vision board goes, but what I'm guessing here is that we have LEDs connected to the MIPS here, and then we have the night vision board connected over here to the camera processor with GPIOs. Hey, Tuco, do you want to play Bolt? I know, you've been yelping. Hey, little dude. I know. This is one slobbery Bolt. Oh yeah, he loves that. Oh, and so this RT3352 also has a lot of other stuff in it. It has Wi-Fi. It has a whole other Ethernet switch and hub, or like Ethernet switch and MAC-PHY subsystem in there. So it's got its own Ethernet interface for the microcontroller, but then it also has a switch so that the device as a whole can have multiple ports. So there's a lot going on in each of these chips. This USB interface, we can probe that if we kind of chop up a cable and solder it to the board, or my preferred way would be to cut the traces on the board and then solder 2 USB connectors on there. Hey, Tuco. What do you want? Did you bring the bolt back? I missed it. Where'd it go? Oh, I see it. All right. So anyway, this is what we determined on the last stream. We were looking at the board level connections on this camera and just determining what was interesting and what might have interesting trust relationships. So we know that, you know, these GPIOs connecting to the LEDs and the night vision, that's not especially interesting. The DRAM is interesting, but probably not practical unless you really, really want in and you're willing to start running tiny wires to an FPGA, or just putting this on a custom circuit board. You can do it, it's just a lot of work. And then the Ethernet, that's already external. So the two things that are really easy to get access to that might be interesting are this USB and this SPI. The USB is maybe interesting if you wanted to try to get inside this OV780 chip and load your own firmware onto it, but it's often, you know, unless you actually just want to run a sniffer for logging this traffic as an aid for reverse engineering stuff that's already running on here, you wouldn't necessarily need to do any hardware modifications just to talk to the OV780. You could just get into this and run programs on the command line that talk to it using normal USB sort of Linux interfaces. So the USB is kind of interesting, but you know, it's like there are other ways to get access to most of that information, and the bus is kind of high speed and annoying. So really, this SPI interface is definitely the first thing that would be interesting and pretty easy to access on this board. And so that's just connecting the RT3352 chip, which doesn't have any internal non-volatile memory that I know of. So it's going to boot by what looks like running something in ROM, and then that ROM ends up pulling some stuff out of SPI using some kind of SPI control hardware on here, which may or may not be memory mapped. It might be something that's more of a traditional SPI controller. It might be something that's actually emulating a memory bus using an SPI memory chip. Depends on how many gates they wanted to spend on it. So far, I haven't seen any evidence of stuff that looks like raw memory transactions, so it's probably an SPI controller that looks like a typical microcontroller SPI master. And it looks like it's just being bootstrapped by some ROM inside the system on chip. And that's all just based on what we saw last stream by looking at the timing of the logic signals as the processor boots. So, so that all leads to this flash memory. And we took a quick look at that SPI bus just electrically and from a timing perspective on the last stream to see how it integrates with the rest of the system. So that's how, that's how I know all of that I just kind of conjectured for you. I haven't seen a full data sheet for this chip, so that's all based on just what I'm guessing based on the data that we saw last time. So anyway, that's some more context. This stream is going to be all about this flash memory. So this is how the system on chip boots. It starts out with a ROM pulling, I think 32K or so of data from this flash into RAM, then running it from RAM. That's, in this case, the U-boot bootloader. So the U-boot loader gives us, it gives you an easy way to load the kernel. It also gives you some utilities for rewriting the firmware over HTTP or TFTP. HTTP or TFTP. And I took a quick look at that. It's pretty bare bones. Like, there are some, kind of half-baked commands that they implemented in the U-boot command line for reading and writing EEPROM. So you can hex dump stuff, but you can only hex dump it 4 bytes at a time, which is pretty tedious. So we can take a look at that. But in this stream, we really are interested in exploring different methods of reading out this memory. So as it boots, we're getting U-boot, but then U-boot then pulls everything else the system needs out of that flash memory, since this is the only non-volatile memory in the system. So we have a kernel, we have an initial RAM disk attached to the kernel, and that's where all the Linux utilities this thing runs with are actually stored. We have some configuration storage, which is, when you go into the web interface on this camera and make changes. When it boots the first time, it generates encryption keys. That's all stored in a separate partition on the flash memory that stores configuration. So everything interesting in the system is basically stored in there. And it turns out that this matches one-to-one with, if you go to the manufacturer's website and you download their firmware, sometimes that's going to be packed in some way. But in this case, that's just a raw 8 megabyte image that should match what we find in this firmware. So that's kind of some context about what that firmware is. It's basically the Linux system in a can. It's 8 megabytes for everything that runs this camera, from the bootloader up through the kernel and the user space, all packed into one little chunk. And then it has a section carved out of that for all the runtime settings that need to be updated frequently. Not super frequently, but in terms of configuration instead of firmware updates, that kind of frequency. And it helps to keep that separate from the rest of the file system, both so that you can use a file system image that doesn't need to support writing, and so that you don't accidentally write over stuff you don't intend to on the file system image. Anyway, so this stream, we're going to explore a handful of different ways to extract firmware from this system. So we know that everything that's interesting is stored in this flash image. And here is, oh, hey, Tuco. Do you just like being right up there in the way, little cat? All right. So anyway, I think we have a slightly more organized version of the next stage of the notes here. So yeah, here's what I thought we could do this time. So in terms of getting the firmware out of this flash memory, so the easiest way to do it, honestly, doesn't involve any hardware hacking other than just attaching the serial port. So we have a serial port, we have a console. We can just send the firmware image over the serial port. It's a little bit tricky given the sparseness of the tools we have available, but as long as we have CAT, which is usually there are probably ways to do it without CAT, but we are lucky and we have CAT. We can look at the tools that are available, but I think we're going to find kind of a weird set of things there. So I figured we'd first try a couple of software methods to get the firmware off, but then try a couple of hardware methods. The thing that seems like, the most versatile method, like the thing that I'd really like to have, or like to always try first in this context. Oh, we don't really need that black square today, by the way. I'm going to struggle to pronounce the nickname. AnaraJB, I think, asks, why would they not have CAT on a BusyBox? Well, you can turn on and off pretty much everything in BusyBox. Like, this BusyBox doesn't have DD because I just didn't need it. So, you can't rely on a lot. BusyBox is designed so that pretty much everything is optional. But I suspect they might have used it for some of their own shell scripts, and so they might have included it. So let's start out. I wanted to try using a Raspberry Pi for some of this later, but for now let's just do it from, since we're using a USB serial adapter, you could do this from pretty much any operating system. I'm going to be using Minicom on macOS, just because that's what I have convenient. Oh, it might be that the driver for this serial adapter is really terrible. It might be that I have to reboot this machine. The prolific driver on macOS is really bad. So we have the device. Do we have an extra copy of Minicom? Ah, jeez. I think I might need to reboot because of the serial driver crashing. That's annoying. Can I fix it by unplugging this and plugging it back in? Nope. Let's reboot. Great. That's what I wanted to be doing on this stream. Last time this happened, I had to actually push the power button on this Mac. It wouldn't even reboot. This is also why I was tempted to just do this part directly on a Raspberry Pi. Maybe we'll just do that. Because I wanted to use a Raspberry Pi for the hardware-based extraction after this. But, yeah, so apparently, as Chris is saying in chat, this happens on Linux too. Yep. All right, I've got to find the power button. Is that it? All right, what can we do while that's booting? Yeah, let's do this on the Raspberry Pi. Yeah, I know. I know I shut it down because of a problem. All right. Do we have cat, or are we just gonna have shoulder cam? I don't think we have cat, but maybe hallway cam is better. Okay, so this is just a Raspberry Pi that I was previously using for RaspDancer experiments, but that's fine. Here it is over on this part of the desk. Oh, hey, cat. Okay, well, let's find the relevant pinouts and get this connected to serial. Oh, I might have one of those little doodads with the pinout on it. Does this fit? J8. This looks right. quite fit with this case, but I don't think that's a big problem. Alrighty. Now I'm forgetting which direction these are. I think this is relative to itself. We need some female-to-female jumpers. Let's use these. All right, so this is just replicating something we've done in the past, which is just attaching the serial port, but this time we're attaching it to a Raspberry Pi. So, power's off. Let's have my anti-static strip not be in wireless mode. These female headers are very stiff. I think that did it. Let's plug the other end in. Oh, that works out fine. Ground, and then receive, which I should hook up to transmit here. Oh, what do you know? These are in the same order as these 3 pins in the Raspberry Pi. I wonder if they used a Raspberry Pi. Doubt it. All right. Let us have a terminal on the Raspberry. Let's have Minicom. I think I'll want Minicom and Pi Serial. Control A. Why do I not have my... Just figuring out which escape sequences work on a new instance of Minicom. I think I might have actually just logged up the keyboard somehow. Yeah. Control A is A. Okay, I just must have hit something by accident. It was probably like X off or something. Anyway, let's set that to. Yes, I always forget the. I have 0 muscle memory for Minicom, it turns out. Okay, let's see if that works. I'm going to turn on the camera. It might be backwards. Well, maybe it's backwards. Maybe it was labeled from the serial adapter's perspective. Let's just try swapping that. Nope, I think the problem is elsewhere. Well, let's do a loopback test of the Raspberry Pi serial by just shorting these two together. Oh, why does this say offline? Does that matter? Oh, I think this is hung again. I'm not quite sure how I managed that. Maybe I have a login. Maybe I need to kill the login process on this terminal. Is that where it is? I thought it was init tab. Maybe this is in Raspberry config. Ah, nice. Maybe it was already set up correctly though. So, and I think I already had this on, but this is also necessary for something we'll be doing soon. Let's just make sure that's the way it's set up. Doesn't take long for this to reboot. Alright. Is this any better? Do I have that installed? I just want to make sure nobody else is using that serial port. And this will let us check who else is using a particular file. That's the serial port. Nobody else is using it. Great. I still have that loopback plugged in, and this is still not looping back. Let's try not Minicom in case this is just a weird Minicom problem. Let's just try using screen. Minicom is a very quirky program, and it's possible there's just something configured incorrectly on this particular Raspberry Pi setup with Minicom. So I think we can just do something like screen dev tty ama 0. That's the right. Am I in the dial out group? Yes, so I should have permission. I think that's how this works. Oh. I guess I would need to install it first. Oh, dterm. Is that what I should be using? I've never used dterm. Let's check that out. Maybe once this finishes installing. How does this help? That's not what I'm looking for. That's a Mac app. I have a terminal that works fine on my Mac. That is 0% the problem. Yeah, that's still not working. Interesting. What's up, Tuco? Oh, am I just misunderstanding the labels on this breakout? Maybe that's the problem. I don't think so. But let's double check the pinout here. That would be the simplest explanation. That's where I'm connecting. I'm using this TXD, this RxD. I'm just going to try it without this little breakout thing in case that's preventing this from making a good connection, but I really kind of doubt that. That really should be a loopback. It really is not a loopback. Why is that not a loopback? No, that was not what I meant to do. Fine. Is that not... Is there anything interesting in dmessage? There's the UART initializing. Nothing else UART related. I guess there's another UART that they're using for Bluetooth. And I'm assuming it's TTY-AMA0, but maybe I should check that out too. Is this going to have the easy documentation? Yeah, that's what they're telling you to do, TTY-AMA0. Scope time, maybe? Well... TTY1 should be on the HDMI output, or wherever that's going without a monitor plugged in. I mean, is this something related to an earlier experiment failing? Would rebooting helping this? Or would rebooting help this? Let's go probe on that loop back. That clip is not going to really cut it. Can I get another jumper in there? I just want something like this. I think that's all right. That's looking like a good sign. I need a pseudo for this to scream. Don't see anything. Is this Raspberry Pi just having problems? I could try a different Raspberry Pi, I think. This is a Raspberry Pi 1. I really think my Raspberry Pi is toasted, but I was hoping I had a second one spare that I could test it with. Oh, Tuco found a good spot. Well, let's try just getting a stream of data going over there. No. Is it just in need of turning off flow control? Is that what this boils down to? Should I just give Minicom another chance? That's not a good sign. Oops. Ah, what did I do? sure how I did that. So, okay, so that's still busy. Screen does not seem to be running. Okay, well, if I reboot it so that it isn't busy, maybe I can open it up and then turn off flow control. Can STTY open it? That's better. Dash F, and then I think that's what I want. It just doesn't want any of that. All right. Oh, I'm missing some good hints from chat. Apparently the TTY may have moved on the Raspberry Pi 3, which is what I'm on. Let's check that out. Oh, they changed the way the orders clocked, apparently. Oh, geez, this is more complicated than I was expecting it to be. Well, maybe I should find a Raspberry Pi 2. I know I have one, I have to pull it off of a different experiment. TTY-S0, is that a thing? Yeah, if TTY-AMA0 was the Bluetooth, that might explain some of the things I've been seeing. If, like, it was being used by the Bluetooth HCI driver in the kernel. Is that a real thing? I mean, these are all going to be graphical TTYs, if I understand right. Yeah, Peter's saying TTY-S0 should work. I don't see TTY-S0 though. Hey Tuco, you joining me over here? It's possible that my Raspbian is too old. Cat entering cleaning mode. Alright, well, this is annoying. Yeah, so I think this moved, but I might also need to update my Raspbian. Is that a real thing? What is RPi update? I've never used that before. Firmware. Man, this is definitely far from what I wanted to be working on. Let's just try this older Raspberry Pi. This might be slower when we start doing SPI experiments later, but it should be fine. Let's see if I can just use the same SD card. Well, this one's probably got an install that works fine. Maybe I'll just leave the SD cards be, since this is probably still what I want to be using for the, what is this thing called again? Raspdancer. That's what I had this originally set up for. Okay, and this is a long defunct experiment using the ENC28J60. So let's just take this apart. This off. This is the network adapter that we were using from the Raspberry Pi's SPI port, which we'll probably have to go in and turn off. There's a bunch of jumper wires that might be handy. This is a Raspberry Pi on one side and a breadboard on the other side. Maybe watch this thing boot so we can at least get its IP address and all that. I don't remember what I called this one. Try giving it HDMI. And we'll be ready to give it power in a sec. And I'm also going to have a keyboard handy. Alright, this should just switch over when I plug this in. I think this is a Raspberry Pi 1. You know, we might as well just do this on the Raspberry Pi. Just get a little more screen. Oh, you probably want network also. Let's plug the network in. Oh, Pibo, that's what I called it. Named it after the case it's in. Okay, well in that case, maybe I'll just reboot it and see if I can SSH in, because it is a little nicer having a real computer rather than like a full screen terminal. So let's take away the HDMI and the keyboard. throw the keyboard at something. Oh no. How did that even happen? No, copyright bots are gonna have me for dinner if I play any more of that. I seem to be really good at accidentally turning on the music, but then I can never figure out which actual key triggered that. I think the problem is there's a setting on macOS that controls whether or not you need to hold down function for the keys to act as function or the audio keys, and it's set differently on a bunch of the machines around here. Alright, so let's go back to the Raspberry Pi. Maybe we can work around the problem where the Raspberry Pi 3 doesn't have a working serial port. I'm not sure I know what the password is, or if it has MDNS at this point. It does have MDNS. I didn't set the password. Let's go set the password. I'm gonna have to check my password manager to see if this has something. Okay, I do have the password for this one. It was another long random one. Great. So I don't think we actually need that. I had to even type that right. Might also just be so long I can't actually type it successfully. Always unexpected technical issues with these. I'd been spending a bunch of time trying to get the audio setup working better, but then I have Raspberry Pi problems. Well, I guess maybe the password on here does not match what's in my password manager, which maybe means we have to reinstall the Raspberry Pi. We could try to crack the password, or we could just change the password. But it might just be easier to reinstall it because I don't really need anything that's on this one. So let's just download that. That also makes sure we have something up to date. So let's just grab, I guess we can grab this. Might as well. Well, although actually this is a pretty slow Raspberry Pi, so maybe I want the light version. And this is a 32 gig card. Let's get a card reader. So that's downloading. It'll be just a couple minutes. So that is what we were erasing. It is disk 4. Yeah, I wonder how much random Pink Floyd it takes to get the copyright bots mad at you. I'm not even quite sure how I did that. I really just need to figure out how to disable the media keys on all the machines and then just not accidentally re-enable them anywhere. Whoops, I didn't mean App Store. I guess I might as well use this. I mean, the volume controls don't really do anything on this machine anyway. Yeah, this doesn't have good volume control on it, which is probably fine. I can control the volume elsewhere. It is so close to done. There we go. So we're sticking that on disk 4. There's our image. There we go. Alright, so that will write our SD card. Shouldn't be too long because this is a USB 3 writer, but oh, there's some discussion in the chat about different ways to bootstrap a Raspberry Pi. I'm also reminded of different ways to bootstrap like an EC2 like cloud instance or something like that. I had this project a little while ago where I needed to just make a bunch of, like basically make a render farm instantly appear and then disappear. So I think there is an option where if you're using Amazon EC2, you can just attach a shell script to the metadata for a VM and it'll run that as soon as it gets to some point in the init scripts. So I ended up using that to apt-get all the rest of the stuff it needed and then do the rendering and then, halt. All right, so let's try that. And we will need the Raspberry Pi to have HDMI after all. Okay, well this will be more from scratch than I had anticipated, but that's probably fine. So, brand new Raspberry Pi, several ways to get the firmware out of this camera. Take 2. So let's switch to that. Well, this will switch when I power it on. Single core. It's charming how the HDMI switch just kind of ends up flinging bits of random memory around. I don't know whether that's the switch or the capture device doing the weird glitches between channels. I think it's the capture device because I don't see those on the monitor here. Some folks in the YouTube chat were appreciating the random Pink Floyd. Yeah, no, it would be great if I could just keep playing that, but that's just like copyright bot bait. Okay, so now we're back on TTY1, and I'm not going to bother setting up a custom login since we're just on the local console here. It's just this Pi and Raspberry by default. Okay, so we're here on the console. Let's run raspi config to get a few things set up. So it already resized the root file system. We also want some interface options. So we want to enable SPI, which we'll use later. And for serial, we want to disable the login shell so that we can use the serial port just for our own purposes. And don't worry about overclocking. I think we can leave everything else. Such a little tiger. Are you not gonna... Oh, there it is. I don't know why that took so long. Raspberry. Great. So we have our Raspberry again. Let's install a few things. Can we just install a bunch of those things? I don't know why I just asked for make without, like, GCC, but sure. I think I want to edit all the source code on the Raspberry Pi console. I think we should probably set this up for network access so that I can use SSHFS and edit stuff on the Mac. So I might just give this the same name. Oh, build essential. Yeah, I always forget the name of that package. It helps to remember it. I mean, this SD card is pretty big, so I might as well install build essentials. Although I might be able to get away with... No, we will need to build some native code for this. There's something I want to do using a native code tool. I was thinking we might be able to just use Python for everything, which we could, but there's an existing tool that will do pretty much exactly what we want with the flash ROM that I wanted to try using. Alright, can we set up SSH on here too? Is that a real package? Open SSH server or Dropbearer. Oh, nice. Let's give this a slightly less generic password. I think I couldn't even type that right. Really? Let's force that. I just want something cheesy for the stream. Oh, right, that was 2 new passwords. I know how to use that, really. Okay, and then spy config, interfacing, turning on and the SSHs. And then set the host name, I think. Pipo. Let's try that. I've certainly had, there's some discussion in the chat about SSHFS being flaky. I've certainly had my share of trouble with SSH-based file systems in the past, but my recent experience with SSHFS has actually been pretty good. Okay, 239, but we should probably have MDNS. All right. That was not the switcher. This is the switcher. All right, I need to take care of that. Okay. Now we are in the Pipo. We can disconnect the local console on our fresh little Raspberry Pi. Maybe now its serial port will work out for us. Let's try that next. So we've got Minicom. Oh wait, 8. I accidentally changed the parity. Gotta make sure not to do that. So that should be right. So I'm gonna just try a loopback test first, like we were doing before. I'm going to stick something in this breadboard between RX and TX. And now we have loopback. Yay, that's what I wanted. So, this is yet another case where I'm wishing I had more, like, longer strips of headers so that I can put one end into breadboard and one end into female headers. But for the moment, I'll just stick with these. So, ground. Then we have RX and TX in some order. So I think we have ground, and then the next one's labeled R, which I'm going to assume means receive on their end. So I'm going to connect it to transmit on this end. And then the remaining one goes to receive, and let's see if that works. Yes, great. Okay, we are now finally talking to the camera using the Raspberry Pi as a serial port. So, I think now we can get back to our first method of extraction. So back to our plan here. So first, let's just look at the available binaries, and let's see what we can use on this machine to get the image out. And so why is that interesting? Well, the firmware we're looking for is in that 8 megabytes of flash, and that, so everything's just packed into that same 8 megabyte bundle, and during different stages of the boot, that's going to be accessed in different ways. At the very beginning, there's probably some kind of ROM on chip that's going to be actually copying a block of memory from that into RAM. And then U-boot's going to have its own driver. But then once we actually make it into Linux, we can still access that flash memory after boot. So that might be how the file system works, although I think the file system is actually RAM-based here. Yeah, so that's just proc mounts. So that's rootfs, which I think is a RAM-based file system. Let's just Google that to make sure I'm remembering the right file system, because embedded Linux has many similar file systems. Okay, yeah, so rootfs is a RAM-based file system that's used by the initramfs. So this is not really like a normal Linux machine where you'd have a partition mounted. This is just operating entirely out of RAM, out of a little bundle of compressed data that was originally stored in MTD0, or MTD, the memory technology device. So that's Linux's abstraction for this flash chip. If you cat /proc/mtd, this is actually Linux's view of this 8 megabyte flash chip that we've seen on the board. So we see that they've helpfully labeled these for us. MTD0 maps the whole thing, that entire 8 megabytes. And these other mappings are actually just basically partitions built into that flash using static address mappings. So this is, I think, the kernel plus the initial file system just concatenated together and compressed. This factory partition is going to be, assume this is something that they log on there when the device is initially tested in the factory. So that might be interesting to take a look at. It might be overwritten when the firmware is updated. The firmware updater might take special care to not overwrite that. Then this config partition is also something that we're probably going to see changes to at runtime. That might be interesting. This is U-boot at the very beginning. So this is what's going to be loaded by presumably the ROM on this chip. So to get the firmware out of this thing, we could just look at MTD0, just cat it. But if we cat it, it's going to go straight to the console. It's a big binary file, so ideally we'd want some tool that is used for transferring a big binary file. So, you know, for example, that's a really disturbing picture in chat. So, you know, if you were back in the days of regularly sending stuff back and forth between devices with serial ports, there are protocols designed for this, like X modem, Y modem, Z modem. You can still find these in, what is it? Control-A-S. So you could send a file with one of these. But that only helps if you have a program on the other end that knows how to break the file up into blocks, send them bit by bit, checksum them, that kind of thing. So we don't have that, clearly. What do we have? We've got BusyBox, which is the, you know, if you look at /bin, a lot of the binaries here are symlinks to BusyBox. If you haven't come across this in the past, this is how a lot of embedded systems save space. So whereas, you know, if I looked at my Mac here, and just like ls/bin, a lot of stuff here, like 23 kilobytes just for RM, 18 kilobytes for rmdir, like, how much of that is actually different? You know, there's a lot of boilerplate code just to deal with command line arguments. There's a lot of structure that each binary actually needs to have. So BusyBox is used to kind of collapse a lot of that overlap that you see between binaries. So it's just a single binary that takes different paths depending on what tool you're invoking. So you can get a sense of what's available by looking at these symlinks, but you can also just ask BusyBox to tell you what's compiled into it. So here's what we've got. Honestly, not a whole lot. We've got some weird stuff here, like, I don't know if these are standard BusyBox commands or if this is something they put in there. You know, there's a telnet server that could be useful, but an FTP server, but not a whole lot. There's artping, which might be fun. But for example, there's no DD, so it makes it a little bit harder to copy things around, but there's cat, which is useful. If there wasn't a cat, that would be annoying. So if we look at our plan, there's not a whole lot. Not a whole lot in BusyBox, but if we're just looking around, look at that, there's curl. Curl can sure do a lot. There's also OpenSSL, which is not like something, this isn't SSH, this is the OpenSSL command line tool, but that's something that might be useful. Just looking at the binaries that exist outside of BusyBox, there's PPPD. There's some stuff that they probably added specifically for what they're doing. MP4 recording. So the most straightforward thing to do here is really just to cat it over the serial port. If we did that in Minicom, a few things would get in the way. So, for example, Minicom seems to be responding to some escape codes that it sees on the other end. And just in general, I think we would end up spending more time trying to disable features in Minicom than we really want to. So I think we might be able to have the best results just making a little Python script that does this using cat. So if you can imagine doing something like, echo, and then some prefix, and then cat /dev/mtd0, and then you echo some suffix, then you send that to the serial port, and then you could just receive that on the other end. So, one strategy to do this might be to, I've thought of trying to do this on the shell, you could just have a cat on the Raspberry Pi receiving this, but I think it might be just less fuss to do this with Python. So, maybe we'll just write a little Python program on the Raspberry Pi to do what we want. So the first thing I want to do is just get a file system mounted so we can use a local editor, because that'll be a little bit nicer. I think we just want that, and that, and that. So now we have an editor on the Pi locally. Oh, it's starting to get chilly. Okay, not much yet, but let's make a file here. I need to refresh this. Refresh folders. Oops. For some reason in the project menu. Okay, and we want PySerial, which we have. Oops. PyDoc would be on the command line. This is, yeah. So anyway, I think we want something like yeah, that's what we wanted. So start this out as a Python script. There's our port. And as soon as we open this, we're going to end up getting a buffer such that if it starts writing back to our port, then we'll be able to catch that data eventually. So then the next thing we just need to do is send it the command that'll end up reading the file we're interested in. So I think we can just use so one thing that you sometimes have to watch out for with this is if you write, it doesn't have to write the entire buffer. It can write just some of what you gave it. So for example, let's have a response let's try writing something really big. Let's just a bunch of spaces and 10 kilobytes of spaces. So that worked, it wrote the whole thing. I think either this means that PySerial has a wrapper that writes everything. That might only be an issue in non-blocking mode, actually. But that's something to watch out for if you're using the serial port in non-blocking mode. In this case, we shouldn't have to worry about it. So in that case, we just want write. Is /n enough in this case, I wonder? I think /r/n might Let's just send that just in case. Depending on how its console is set up, the line endings might be different, but this should always end up giving you at least one line ending and some white space, which the shell should be okay with. And then we just want to echo something that'll signify the beginning of the image, which we'll probably just end up cutting off, but it might be useful to have this for just checking purposes. So let's just do that. So prefix, let's have it just randomly generate these maybe. So we can use random.choice. Use string. Printable, why not? Oops, that's off the edge of the screen, sorry. Something like that. Let's just see if that's working right before we go too much further. Make it executable, and let's, was that including like /ends and stuff like that? I think let's maybe not use all printable characters. It doesn't really matter, I just want it to look alright while I'm debugging it if possible. You know, when I'm searching for something in a sea of junk in the hex dump. How about uppercase? Yeah, that's probably what I want. So, and then let's have this send a little tiny shell script. So we're going to do one echo. I only need the command option that cuts off the new line. I don't need to interpret backticks. I think that's /n. Yeah. So echo /n, then cat our file. That's what we're actually trying to read on the target. And then another echo. So that's what we're telling it to do. And as soon as this command starts running, we're going to start getting stuff back in our receive buffer. So we'll just have to start putting it somewhere, and my thought is we can just keep receiving until we see that suffix and then chop off the part we're interested in. So you can clearly make more of this clean with like command line arguments and stuff. I'm just writing a really quick hacky script for this. So then we would probably want to start reading this in blocks and start checking for the suffix in each block. So I think let's read something, and then let's make sure we can read the output file, or open the output file, rather. So we'll just start writing that to the file as soon as we get the relevant stuff. And then in between blocks, we'll need to keep track of whether we found the prefix. Well, let's cut off the prefix later. You know, this will easily fit in memory, so I'm going to make things a little easier and not worry about that until later. So let's just accumulate all of this in a buffer. Something like that. Sure, let's just print the total like that. And then if this block or the previous one contains the suffix, so we'll just look at the end of this buffer and assemble it into something contiguous. And then look like that, if that. Okay, so that should give us the whole image here. We just have to chop off the part we want from in between the prefix and the suffix. So we should be able to do that. Just doing some stuff like this. Image. So we'll make that linear again with all the blocks this time, which will give us a big old string. Then so we'll be doing something like that, and want to make sure these are both found. So something like that. And our actual image should just be in between those. Like that. And let's try that and see how terribly it breaks. List. Oh, geez, that's a bad typo. Appending a whole copy of itself each time. So I might need to go in there and stop it from whatever it's doing. Control C. Yeah. Okay. So that might be working. Hard to tell just yet. How many blocks are we dealing with? A lot. So this will be probably the slowest possible way to get the firmware out of the device. I think I might have this. Let's try this out on a smaller file first, just to make sure the method is sound. So let's make the local file. Let's just get a copy of the BusyBox. So Control C, make sure the system's fine. Cool. This would be nice if it let me inspect the contents as it was grabbing it, wouldn't it? I was about to write a little state machine here that would keep track of whether it had seen the prefix block yet, and if so, would start writing things to the file. This is a little bit simpler to write, but means you don't get the file contents until after the whole thing is downloaded. BusyBox is probably pretty big compared to because it's not compressed. It's going to be like a half a megabyte probably. So maybe like 128 blocks or so. I can't actually just use the console while it's transferring data, but. So anyway, assuming this works, which is a dangerous thing to assume at this point, but, oh, is that it? Is this the Raspberry chunking away on that string now? Did we not get the suffix we were expecting? That could be annoying. Let's try this with more debugging on a really small file. So what do we have that's really small? bin/i2c is small. There's probably some really small stuff in /proc. How about just procmtd? So we can change remote file to procmtd. And then local file would just be mtd.txt or something, sure. I want to see what this command is, and I want to see what all the responses are. Of course, there are so many ways of debugging this. You could attach a logic analyzer, but right now I'm just going to use print. Oh, maybe this is going to block until it reads all 4096 bytes, which is not what I wanted, actually. I think I need to give this a timeout. Oh, timeout is on the whole port maybe, or do I need to set timeout? Yeah. I think I can also do that when I open the port. Let's do that. That's not the cleanest way to do it, but it'll work. It didn't strip off the header, but the rest of this. Oh, because it got an echoed. Oh, it got an echoed copy of the command. That's funny. That's funny. So maybe I should encode this with backticks. Do I have echo-e or tick-e or dash? Whatever you want to call it. Let's do that. That is being decoded by echo and not the shell, right? Oh, that's the shell. Let's just do that then. Except that will not work for all the characters we want. Just don't want the whole thing to appear in there. We can mangle it pretty much arbitrarily. guess we could do hex. That's what we wanted. Let's just do that. That's easy to do. Just going to clean this up very slightly. I think we want something like that to escape it. And then making this slightly more complicated, but this should be right. How about that? Echo encode. That's ugly. Did it work? That looks good. That is a file. Is it clean at the beginning and the end? Looks like it. Let's try sending a binary file. Let's go back to Minicom and look around. Something kind of not too small, but kind of small. This one maybe. H.264. 25148. It's retrieving our little application. 25274 this time. That doesn't seem like it was the same size. That's not the same command I meant to run. That's not the command I meant to run either. I meant to SSH or run back into the Minicom shell. 25274. Yeah, our binary is a little longer. So we might have had some like CRLF translation or something like that going on. So we might have to do something to either change the shell settings or to undo that translation. So we were supposed to get a file that's 25148 bytes long. Let's save that over here. So, just out of curiosity, that looks like it. So maybe we just do the inverse transformation. Because there are obviously ways of disabling that, but I don't know if there's a good way using just the tools we have available. So it's probably easier to just transfer this, or translate this back. hoping that there isn't a translation for just bare/rs, because that would be ambiguous, but let's see how far that gets us. Oops. Let's run that again. Two, 5, 1, 4, 8. It's an elf. So the real test would be, you know, does it disassemble quickly? Does it line up after, like at the end? It might be worth grabbing the firmware image this way to compare to the other firmware images we'll be downloading. I don't know if I want to do that whole thing on air just because this is a really, really slow way of grabbing the firmware, but this should work out fine. Like, we can grab arbitrary files this way. There might be other things in this kind of terminal Rube Goldberg machine corrupting the text, but assuming we've figured out all of those, then we have a way of reading arbitrary binary files from the device. So if we were to do this for the flash memory, we would set this to dev mtd0, so it's reading the whole memory, and then we could just set this to mtd0.bin. And now it's reading the flash memory pretty slowly. So we could potentially see the, like just see the data on the bus on the SPI flash. But if we're limiting ourselves to a mostly software approach, this is maybe the first thing I would try, but it's also really slow. So if you want to try this, if this is the only option, but if you have a lot of patience, then so there's that. Oh, and yeah, a couple of questions on whether there's any kind of hashing binary on the camera to see if things are correct. I didn't see one. Oh, there's the OpenSSL. You could probably use that to compute a hash. Let's see if we can do that. Digest. So can I do SHA-1? What is SHA? Oh, this is all the SHAs. Ooh, we could do SHA-256. Binary, or no, we want output in hex. We want the input in binary. I think the input comes in on standard in. So maybe this. Yeah, we could try running that on both ends. I'm not going to wait for this. This is going to be very, very slow. But let's just try to see if our tiny binary made it through. So we did grab that h264.bin, which is a binary we might be interested in reversing. So we're using OpenSSL because that's what's available on both sides. h264.bin. All right, and let's grab our minicom shell. Oh, stop that. Command is still there. With our random headers and footers. OpenSSL, cool. It looks like a match. Oh wait, no, maybe it isn't. Let's put these side by side so I can actually tell. I was just looking at the beginning and end, which is usually enough. Oh, that's a match. Great. So that verifies that this script is probably fine. So let's save this for later, maybe. Might run that later on if we just have some time to kill, but it is among the slowest possible ways we could get this done, so let's save this for later. What did we call this again? serial get.py. Oh, let's just actually copy that from the partition. Okay. Well, I think that concludes the first of the various methods, which is downloading it carefully over the serial port. So this is something that you don't necessarily find just off-the-shelf tools to do because it's not really a good idea. Normally you would have, a protocol like zmodem on both ends. But if you don't have that, and you don't really want to go to the trouble of trying to compile the right zmodem binary and stuff it on there, then, oh, that's a good suggestion from Robert. If there's OpenSSL, then OpenSSL might have a command that can encode it. So yeah, a lot of what we're doing here is kind of being very paranoid about the parts of the link that might mess up binary traffic as we're sending it through. But if we can convert it to text, then we can just like copy and paste it or whatever. It's a little easier to deal with. So we have various ciphers. I'm wondering if maybe you can have it do like a pass-through and then like hex encode the results. Yeah, that might be possible. I don't see a way to do it off the top of my head, but that would be worth looking into for sure, like if you want to convert things into an ASCII format. But at least so far, it's nice to have something that we can use as a digest. So while we're on the topic of interesting tools that exist inside the camera, it also has curl. So I think another method we could try is using curl to extract the firmware. So curl. We have this curl binary. Curl is a command line tool for doing HTTP requests. So if we get this on our network, then use curl. We can send the firmware as a post data to something else, and then, it doesn't even have to be a real HTTP server. We could just use netcat. Speaking of netcat, do we have netcat on here? We do. And over here we have curl. Can we run curl? So I had this problem before. I don't know why they have things configured so the curl normally does not have access to the libraries it needs. But the way I had been working around that was just by copying some libraries. So we have, also it does not have ln for creating symlinks. So it doesn't have ln, doesn't have move, but it has copy. So I've been copying. Oh, Mike Matisse says OpenSSL should have a base 64 mode. Is that a thing here? Ooh. That looks like a thing. Do I have that on here? Yeah. Why was that not in the help? Or did I just miss it? Yeah, okay. I don't see it in here, but... Oh, there it is. It counts as a cipher. Okay. Well, great. That's super helpful. So let's just demonstrate how that would maybe work. So for that, you could actually just stay here in the comfort of Minicom, and from here you could turn on logging. Control A. Let's see. Control A L, and then it'll start capturing to a file. And if you look at the Pi on another console here, we have that minicom.cap, which is currently empty. Then we should be able to do OpenSSL base 64, and then redirect dev mtd0. So now this is going to restrict itself to characters that Minicom won't have an adverse reaction to. It'll still be really slow, but now we're capturing that into here. And if we just manually cut off these lines now, we could feed this back into OpenSSL and unbase64 encode it, and we should get our firmware back. And this is, it's much easier to tell when something goes wrong this way, since you'll have lines that aren't all the same length. You'll have characters that aren't printable, that kind of thing. I think this is FF's, like, cleared flash memory. So that's very helpful. That's definitely another useful way to get files out of a device if you're lucky enough to have a tool like OpenSSL around, but unlucky enough not to have like UU encode or Zmodem. So I'm not going to let that download the whole thing, but that would be one way to do it. Let's try using curl next. So we'll need to make curl run first of all. These libraries are there, they're just not symlinked correctly. And we don't actually have a symlink tool. So I guess I could copy that symlink. I was just copying the file. Actually, I don't know if the CP in this case will copy the file or the symlink. This wanted SSL.0.9.8, which is not quite what we actually have on the system, but I'm going to just copy them and hope it's compatible, which I think worked last time. And a similar issue with libcrypto. And this is all going to go away next time we reboot the camera because it's in RAM. There might be something in one of their setup scripts that does this. I don't know, or they might just not even use curl. This might be left over from something for debugging, so I don't know. So anyway, now we have a curl that works. Are we on the network? We are on the network. This is an address on my LAN here. So we should just be able to have these talk to each other. If we do netcat, and just have this listen on some random port, and then save that in a file. Let's call this, what do we have here? Yeah. mtd.http. And now if we do curl, this has lots of options here. We want to send a file as binary post data. So we want data-binary. And then if the argument starts with an @ it treats it as a file name, which is what we want. And we can just have it read directly from dev mtd0. And we want our Raspberry Pi's IP address here. I think that'll do it. I think we're monopolizing enough CPU time that the sound card is having buffering problems now. So if we get another shell, we might be able to see that file filling up. Oh, it looks like maybe done. Let's try Control D here as an end to file. Okay, cool. So we didn't Control C because that might have deleted the buffers while there's still stuff in there, but Control D sends an end to file to the other end. So now curl just thinks the server like stood it up and never actually responded, which is fine. I don't really care what curl thinks at this point. But it had already gotten through sending the whole HTTP request, which should have the data we care about. So now we can see we've got an HTTP header, starting with this post, user agent, and all that, content length, content type, and then right about there should be the beginning of our image. And then at the end of this, what do we have? It should just end. We might have like a spare CRLF at the end. Let's hex dump this into a separate file so we can seek around a little more easily. Oops, that's not what I wanted. HTTP. Need to clean this up slightly. mtd0.bin is not a real thing. that's better. Oh yeah, people who, I mean, there's a good point in the chat that anybody who, like, if I were to do this in production and then like ship it, then people would be really mad to find a mislabeled libSSL binary. Yeah, don't ever do that in production. I'm only doing that to get this working. But like, if you do that in production firmware, you should feel bad and you should fix it. Okay, so there's the beginning and there's the end. So I think that is the actual end of the firmware. I don't think we have a spare carriage return or anything, which is good. So let's try trimming this and see if it's the right size. Let's see if we can just trim it in Vim. Oh, I don't have Vim installed. Vim is handy for this because you can edit binary files relatively successfully. The Raspberry Pi is an ARM. The camera is a MIPS. I'm also curious what they would be using libSSL for. I don't know if the actual like config console is at all SSL protected. I mean, I'm hoping they use SSL for firmware updates, but I think the firmware updates are manual, so you'd be downloading it from the D-Link website, using your browser, which would be checking the signatures, and then you'd be uploading it to their thing, which would be YOLO. I really got my terminal stuck here. Did that work? I think resetting the terminal might have actually killed, but I guess not. Great. So vim mtd0.http. Okay, so I think this is going to be the beginning after these two. Because if you're thinking about this in terms of HTTP headers, this would be the beginning of the actual post data, I think. The only concern I have is whether or not this last /n is part of the payload, but I'm pretty sure it isn't. Let's just delete all of this. So now let's see how big it is. Is 1 byte larger than 8 megabytes. Let's see if there's anything lingering on the end. We're still hex dumping. Maybe I'll use my pre-hex dumped copy because it's a little slow on this old Raspberry Pi 1. EC. That seems like it's part of the image. Could that single quote have gotten in there? looks potentially aligned. Well, at this point, I'm going to cheat slightly and start checking this against some images that we have via other means. So I mentioned that in this case, we have an image you can just download from the web. So I've actually already got a copy here, but I think it might be worth just going through the motions of how you would get something like this. So first, I'm just going to Google for the product number. There should be a support site. And I'm going to try to get the specific version that we have here, which is 1.13.05. So now we have this download. It's a zip file. And we have some release notes, and that .bin, I think we'll find that it's exactly 8 megabytes. Yep. So this is actually the image that goes directly onto that SPI flash, and so that's what I've already extracted here. And I've already hex dumped it. So that SPI flash image tag should be lined up with a 16-byte boundary. And that's what we've got over here. This information up here I would expect to be different, I think. I think some of this changes during normal operation. It does start with that tick in both cases, that 2705. So what about the end? I think maybe, oh, there it is. Oh, why did I not notice that last time? Okay. There's my missing /n at the end of the file. That's what I would have expected with the file being lined up, but just 1 byte longer, but I didn't see that last time. Okay, so there are a number of ways to trim that off. I'm just going to use head. So we can use head with a character count. 8388608, mtd0.http, and then I'm going to just save this somewhere and then write it over mtd0.http again once I check it. That looks right. Yay. So I'm going to stash this on my Mac here so that we can compare it against the other images in a bit. Okay, so fw.tail. Okay, these are dregs from the last time I tried this experiment, so we can delete these. Okay, so we've got our serial get script, we've got the original firmware, and that mtd0.http is the one we received through the web server. So one thing we can do, we can go back and get a hex dump. One reason I like having the hex dump as a separate file is then you can diff those. So for example, I think I want these set up side by side. So we'll have the manufacturer firmware image on the left and the stuff we just pulled off on the right. So the stuff at the beginning is different. I think this might be indicating status of the bootloader or status of the logging partition. So what's actually different? This word is different. This word is different, but not this one. So these might be something that has to do with each partition in the flash memory. So then we have the bootloader image. So let's look for just things that are different. I'll look for that pipe character that separates differences. And I'm going to look for it with spaces around it. Oh, maybe tabs? Huh. What is actually on the screen there? Maybe that is a tab. Now I'm forgetting all the Vim regular expression bits that I would need for this. What actually is on the screen right there? So that's a space, a pipe, and then a tab. And I still can't quite search for the tab, I guess. But just the space and the pipe, it's easy to match. Whatever. This would make things so much easier if I could just remember to match tabs in a Vim regex. Oh, that's a good tip from Robert in chat about how to do the hex dump inline on one command line. /t, that's not what I want. Whatever. Okay, let's give up on the side-by-side for now and just see where the actual differences are. Okay, so we've got that line in the very beginning, like technically in the bootloader section, although I imagine it's being used more like a partition map. Then this is later in the bootloader. Not sure what that would be. Oh, or maybe that's, well, let's take a look at that, that map we had. So the bootloader goes until 3.0.0.0.0. So this is in the config, the config section. So this was erased, and now it's got all sorts of config text in it that's being logged there. 3.200. Web init. Yeah, so this is like a key value store that it's using for non-volatile storage. Admin password? Is that just blank? So, I mean, obviously this stuff is going to be privileged. If you can get to the point of reading this stuff, then you have the private keys, you have the passwords. This is how the device's whole identity is stored. So this section where the configuration goes has changed a lot. It started out blank. It's been formatted, and it's got a bunch of this stuff written to it. Just a lot of default variables, mostly, but also private keys that it's generated at first boot. Yeah, these are the keys. Then, what else? This is down where now? This is in the factory partition, I think. Not sure what this would be, something from factory testing that maybe the firmware update tries not to overwrite. But everything past that, so past the config and factory, all of that checks out as identical, so that's what we would expect. So, firmware image, downloaded from the web and extracted over HTTP, and we've at least shown how to get it over serial, even though that's really an overnight job at 56K. So, what else is next? I think that is pretty much all the software extraction methods I wanted to try. I think the next method, let's go back to our notes real quick, but if we looked at the binaries, we tried a Python script for doing it over serial, we used curl. I think we're right here. I want to try to passively capture it over SPI and hardware. So the nice thing about this is that you're not kind of fighting the system on chip for the SPI bus. If you were to just directly read the data out, you'd either need to desolder the chip or hold the system on chip and reset so that it's not also trying to talk to the SPI, or you just need to connect both SPI hosts and hope that yours has lower impedance drivers and that you aren't damaging the other chip too much. So, you know, the kind of fighting it for the bus is less optimal. So we could try to read it out using a Raspberry Pi. Ideally, we'd find a way to hold the CPU and reset, but if we don't find that, we could just fight it anyway and see if that works. We could also pull the chip off the board using hot air and then read it using a Raspberry Pi or an Arduino, but I think a Raspberry Pi is a pretty nice way to do this. There's a tool that I wanted to try using on the Raspberry. Do I have it handy? How did I already lose that browser window? There is a really simple SPI Flash programmer. Here it is. So it's flashrom.org. It's actually a nice little tool that is mostly targeted at people who want to flash open source firmwares on their laptop or on other devices like that. But it seems like a pretty good match to our case. You can use it with the SPI interface built into Linux, so we should be able to run it on a Raspberry Pi using its SPI port to talk to the flash. And it supports a lot of common flash chips, so I think I want to try that next. But before we do that, first I want to just try something passive. So without any modification, you know, we'll still need to attach to the flash memory, but without actually taking anything out of circuit or holding anything in reset, then, oh, and Robert mentions in chat that this is also used in coreboot, and yes, for sure. That's the other page I found with a lot of information on here. So this page from LibreBoot, which is, I think, this used to be called coreboot. It's an open source firmware for laptops. So this actually has some good information on exactly what we're about to try. So with the exception of this is not a laptop, this is a digital camera, or a web-attached camera. But we're basically doing the same thing. I think they're using... So see, they're powering the processor. They're just powering the entire laptop through the 3v3 rail that they're getting to via the flash chip, which seems a little sketchy, but I assume it works. It's just there's a chance that you damage some other hardware on the board doing this. There's also a chance that it just sucks a huge amount of power from this 3.3 volt rail and most of the system powers on. So that's not the best option, but it's much more convenient than the alternatives for sure. So let's try this next, but the first thing I want to try is passive. So this avoids doing any of that modification. All we're going to do is boot it up normally, maybe just for good measure, just cat all the flash into dev0, just so that we're sure it's all been read. And then we'll go through and look at the logic analyzer logs and piece the flash image back together. So there are a lot of different tools you could use for this. I'm going to be using the Salia Logic and the Logic 16 software and exporting it to a text file, and then we'll write a little bit of Python code to put things back together. So I've already got the logic analyzer set up with the 3 channels that we want. This particular one, so the rate that we're sampling at, This chip usually talks to the SPI flash at 16 megahertz, but it bumps it up to 32 megahertz for portions of the transfer. So sampling at 50 megahertz, you won't always get all the clock edges. So we'll definitely need to be able to sample at 100 megahertz or around there. And to get that rate instead of 50, you have to have 3 channels or less on this analyzer. So 3 channels. That leaves just enough room for chip select clock and data output. So that's what we're going to be logging. And there are, again, a lot of ways to actually make the connection onto the board. You can get these little spring-loaded clips that just fit right on top of whatever chip you're dealing with. So if you're doing modifications on one particular device often, or you want it to be fast, you can get a clip that just clips on there. In this case, I'll be using individual clips that just attach to each pin we're interested in. And these particular ones come with the Salia Logic Analyzer. You can also get them separately. You want the ones that have 2 little tiny metal bits that lever around the wire, instead of, like some of these, you have just like one little metal bit and it levers the wire against a plastic housing. This has 2 little bits. If I can demonstrate with something it'll grab. So you want something like that. Gets a nice solid grip around even the tiniest of wires. And I think we already had a pinout for this chip, which I might have deleted. Let's get this again. So it's a WinBond 25064, Q64 rather. I think this is the same one we used before. This is the chip we want. So we want the 8-pin SO, this one. So ground. Pardon the focusing. Okay, that was the serial. Here's the flash. Okay, ground, pin 4. This should be off. I think we want chip select next. Yeah, chip select would be pin 1. This chip also has a 4-bit at a time mode, which is a little bit unusual. From our investigations before, it doesn't look like that's being used, which is handy. We'd probably need a fancier logic analyzer if that was the case. And then clock is pin 6. And lastly, data out, which is pin 2. Do our best to make sure none of these are actually shorting anything before we apply power. Alright, so there's our micro grabbers. So now I'm just going to power this up and do a logic analyzer trace. So this is something to do with a logic analyzer that streams the data back to the PC rather than something with a buffer, because this produces a lot of data. All right, so powered on. Oh, let's get the serial console up here too, just so we can have that handy. can look at how much memory the Salia is using to get an idea of how much data is going across. You know, of course, not a direct map. The data that the logic analyzer stores is much larger than the actual data that is being stored in the SPI flash. Yeah, it is a good thing I wear the anti-static wrist strap while programming. Yeah, you always get it backwards. You wear it while programming and then don't wear it during hardware. Internet.sh. Yeah, see, they do a lot of stuff with shell script, so that would explain probably most of the stuff they do have in BusyBox exists because there's a shell script here that's using it. All right, so we've got this again. That probably touched all the memory we care about, but just to be sure, we can just cat all of MTD0 into a Bitbucket. And this will show up in the logic analyzer log, but nowhere else. And that stuff is unrelated. That's just the camera controller spamming the console. Okay, that's all we needed from the logic analyzer. So we can see that. So that's the bootloader. That's the bootloader loading the Linux kernel. That's a bunch of runtime stuff, probably configuration access. And then that's me just catting the entire device at the end. So I'll be saving this as a text file. This will be in... I don't know what the difference is between their text and CSV files. As far as I can tell, the text file is also a CSV, but maybe the difference is subtle. Maybe it's about whether it's quoted or not. Let's make this more specific. SPI boot trace .text. Usually this takes a little while to save. Why was that so fast? I don't think that's nearly large enough. What's going on here? Did it fail at some point? "20 seconds in? What happened 20 seconds in, and why did it fail to write the rest of the file?" Oh yeah, a bunch of stuff started happening 20 seconds in. Whoa. That's not okay. Okay, I have clock and data backwards. That would be a problem. Let's just fix this. We don't have to recapture the trace, we just have to tell the analyzer what's what. That's better. Helps not getting things backwards. So now we have bytes. SPI is still decoding over here. This is also probably something where using SIGROC, you could probably just have a special purpose tool that just streams this into a file without having to have so much intermediate data. That's certainly the kind of thing I've done before in writing my own tools. Is this really misaligned? What's going on here? Oh, I think I have not set up my SPI parameters correctly. That's right, I did this in the past and then forgot to do it now. Or did I? Clock is high. on trailing edge. I think that's what I wanted. What? Also not that. No. That's the wrong clock edge. That is some weird SPI timing. This is in which mode now? It's 33 megahertz mode. I just want to make sure all these bytes are framed properly. No. This shouldn't be changing on the same clock edge we're sampling on. Yeah, that's definitely wrong. So, valid on the trailing edge. If we saw, if it looked like it was the other way around, then there was something else wrong too. That one looks fine. As does that one. Ooh, there it slipped. What happened there? Is that just noise or like a logic threshold issue? Is this just, oh, what speed is this at? This is 33 megahertz. We should barely have enough sampling to get this. They aren't going to look nice. That looks fine. And then over here, it's fine. Now it's just a mess. That's no good. Maybe more grounds would help. Yeah, I don't know. I'm just gonna plug in another ground in the Salier, and then run this trace again, but I'm not optimistic that'll actually make any difference. Plugged in this one. Alright, let's just reboot this. Where's our terminal? The one that matters. This one. was hoping to do it passively, but maybe I don't have a streaming logic analyzer that's fast enough. So a lot of this boils down to just having a piece of hardware that knows how to stuff the data somewhere useful at the same rate it's being read by the system on chip. And the logic analyzer is going to be kind of inefficient based on how it's just sampling multiple bits and just saving their states rather than actually turning the protocol into serial or into parallel bytes and storing them. There are dedicated SPI analyzers made by Total Phase that would probably be useful for this kind of thing, but I don't have one of those handy. End of internet. I just can't stop pressing enter. Because it's an open shell even while it's still booting stuff. Read the whole thing. All right. So I'll stop that and see what we got. Beach Ball City. Oh, good question from Nick, wondering if the scope could stream it over the network. The way I understand it, the scope doesn't have a streaming capture mode. It stores a buffer full of stuff, and then you can analyze the buffer. It has segmented memory, which you could use to store a bunch of separate segments. Like this is just getting into the territory where like a logic analyzer of any sort would need a ridiculous amount of memory to save this. Which is why I had the beach ball. Okay, so there's our stuff. There's the rest of our stuff. Same deal. There's boot, more boot, configuration-y stuff probably, and then the dev 0, punctuated by some other stuff, whatever I guess was busy. So let's see if this is stay lined up now, or if we just have to abandon this for electrical problems. That doesn't look lined up. Yeah, we're losing clocks. Let's see how that looks on the scope. Maybe we can add some termination or something. That is the red wire. You know, it also occurs to me that I wonder if we'd get a cleaner signal. Like, I wonder if it matters which channel I use in Logic Analyzer. If the one right next to ground might be better for this. Like that one. Just a fast micro with 2 SPI ports. So you'd think that would work, but SPI doesn't really work like serial. Like you have to have, so like if you're trying to emulate a flash device with a microcontroller, you're going to get one interrupt that says, "I've got a byte." That's great, and then at some point you're going to reach this area where, like, right in between 2 bytes, you've got to start buffering the data for that entire flash block. It can work. It just really involves, like, for that to work, you kind of need a bit of a delay in between the address and the data, and usually you don't get one. Like, usually what happens is you've got some piece of hardware that's just going to send you this big torrent of bytes, and unless the SPI actually is slow enough that you can execute code in between 2 bytes in the packet, you can't put the data that is requested of you in that buffer after you know the address. So there's kind of this dependency problem. So it's easy to do if you have hardware and the data is just right there on your own bus. But if the data is far away or you're doing it in software, both of those make it hard. Oh, Mugundan, I think, I'm probably pronouncing that wrong in the stream, but they're thanking us for the stream. That's great. You're welcome. Glad to be doing something that people find interesting and potentially educational and useful. So let's just do another capture. Reboot. I don't really expect this to make any difference, but we'll see. .64 megabytes of RAM according to the bootloader. It's really tempting to not even do this entire test because I don't really expect it to work, but might as well. Might as well let it boot. Welcome to the system architecture department. Every time I boot this, they welcome me into their whole department. You're such a good little cat loaf. Click, click. Light sensor changed to day. I just decided it's daytime in my lab. It's actually not daytime, there are just bright lights here. Joke's on you, sensor. Okay, so it vomited all over my console while I was writing that command, but it should be doing that cat into def null again, which doesn't take that long because it's reading it pretty quickly. All right, now let's killer log. We're gonna stay synchronized this time. Oh, I need to actually attach this to the analyzer. The coder slowly crunching its way through this. That is really, really not getting all the clock pulses I want. Well, let's take a look at it on the scope just to make sure there isn't some terrible signal integrity problem, but it might just be I'm getting really unlucky with the sampling times. Like, if it's not 50-50 duty cycle, I might just be sampling it at really, really the wrong times. I don't know. This is suspicious, and I think I want to see it on the scope. Right down there. And this one. Let's put this. So many wires. Of course, testing signal integrity with a dubious setup is never the best. figure out how much better I need to make the setup if I need to at all in a sec. Very hard to attach a scope probe to a mini grabber. Maybe I'll need a wire in there, even though I'm a little worried about the wire affecting the signal. Tiny male to female jumper. I don't know if I have that, but all right, fine. I'll just take a bit of one of these, cut this in half. Oh, that clock looks weird. Let's get that on the screen. Appears to be continuously clocking too. Or is that just persistently showing up on the scope? Oh yeah, I just have the scope on normal mode. What are we actually dealing with there? That looks like our 16 megahertz is not the super fast mode. We could try capturing a bunch of this in persistent mode just to see what different clock shapes we end up getting. This would be in display persistent, infinite persistent. All right. So this should show us all the clock shapes. Let's reboot this. Oh, let's fix our horizontal. Okay. Looks like that was our, 30-something megahertz clock. Yeah, like a 33 megahertz clock. I'd think that the Saleae would be able to capture that with its 100 megahertz mode, but maybe we just have some signal integrity problems on some of these edges. Terminating it on the Saleae end might help. Yeah, well, I think we can put that approach aside. This would be something to do with a faster logic analyzer or a slower target. But in this case, I think it's much easier to either just read it out through Linux using the various software methods we've tried, or to just read this directly instead of taking it out of the circuit. Oh, so a noob question. Can you read memory directly from flash instead of device to boot. Not quite sure I understand the question. Can I read it directly from the flash instead of the boot device? So the way the boot process normally works on this camera is I think it has some ROM where there's a small program that copies the proper bootloader out of SPI Flash and then runs it. I don't know where the ROM would be. I haven't really looked for it. I assume it's mapped in memory somewhere. Potentially unmapped later, but maybe not. And then this SPI Flash is just connected to an SPI port, so there's lots of ways to access it. Like once the system's booted, you can access it from the MTD devices in Linux. There's also, I should show this on stream, there's actually a little system for accessing it before boot, which we could check out. It didn't seem that useful to me, but if we press 4 to break out of U-boot, so you can see we had this little menu that showed up during early boot. This is put up by that bootloader U-boot, which exists in the first couple of tens of kilobytes of memory. So it has some options for programming Flash. It has some options for programming temporary code to RAM. That's interesting. But what we really want is this command line interface. There isn't a whole lot here. We can do stuff with raw memory. So there's memory display. And this is probably going to be just U-boot itself. Anyway, we have these SPI commands. But it doesn't seem to actually want to do much. So yeah, we can do that. Is that even the first word? Maybe. Maybe it changes every time we boot it. It's similar. But I don't think this actually works. Like, that doesn't look right. So, and then I started looking for the code behind this because this SPI EEPROM dump thing is really suspicious. And I think if you just actually literally look for this message, you'll find the code behind this. Yep. This is U-boot ported to the MT7620, so I guess that's where we are. And this is their SPI driver for the bootloader. So there's some commands here. So you could use this to figure out how to talk to the SPI if you needed to. There's some header files with all these registers. There are enough levels of indirection that I didn't immediately see how to convert these into actual like flat memory addresses, but I assume that wouldn't be too many more levels away. That's the command set it's using apparently. So the read command. So anyway, then I get a little farther into this, and the command line interface they provided for U-boot is kind of just a stub here. So this EEPROM dump is completely just not implemented. I guess they planned to do something there, but no. And then these commands, like this is always just reading 4 bytes. I guess the value's in hex, but it didn't really seem to be interpreting the address correctly. So, yeah, this didn't seem to be that useful. Oh, good question from Ben. When it loads the flash into RAM, it probably copies it byte for byte into a location in the RAM linearly. So if you let it load, then reboot it during the uncompressing, could you scan the RAM space with MD to find the flash? That's a good question. Let's try that. So yeah, so it's probably doing something where it copies the SPI flash into one area in RAM, and then decompresses it into a different area. So maybe we can try that. I might even wonder if we find like spurious copies of it elsewhere if we just have a fresh reboot. But so yeah, so let's reboot it once, and then I don't have a reset signal broken out. Maybe that's a good thing to do next, because it would be nice to be able to hold this thing in reset so we can talk to the flash directly. I was figuring we would just have to overpower the drivers, which is not the politest thing to do. But if we could hold the system in reset, that would be convenient. There are 2 buttons on the board, but I don't think either of them are hardware reset. So right now the clock is idling low, which is interesting. Just resetting it. Now it's idling high. So power off, power on, and then 4. So I did power it entirely off. Hopefully I did it fast enough that the DRAM didn't deteriorate, but that's not the most reliable way to do it. So now there might be a copy of flash in here somewhere. Not probably the entire flash, probably just the kernel. So what are we going to look for? I think we want something around there. Is this going to be a multi-boot header? I forget. There's a specific magic format that Grub uses for headers. I don't know why they would have the same format on this machine, but I'm curious if that's what this is. I also really should have had a copy of the MTD info here. Is that still on the Raspberry Pi? Since I don't really trust myself to remember the right address. Pi. Yeah, mtd.txt. Let's just have a copy of this. Okay, so actually that was the factory partition that we're reading. So we want 5000 or 0000. I don't know of a good way of pronouncing numbers like that are just really easy to type but really cumbersome to talk about. Let's take a look at the reference image to see what we want to find there. That even tells us, oh, let me move this so that it's a little easier to see. Linux kernel image. So let's see if we can find that in memory. Do we have any memory search commands, or are we just going to dump it all out? I don't see a memory search command. This HTTP server is interesting. I tried it, but it doesn't have any documented functionality, at least other than just writing an image to it. Kermit would be fun. Memory modify. Yeah, memory search would be nice, but I don't think we have that. So this would only really work if we got super lucky or if we looked up the address somewhere. It knows where the Linux block goes, of course. I don't think that was useful. I could just start trying round numbers, perhaps. Assume this is RAM. I assume this is probably still a code from U-boot. So we could also just dump out something in the middle here and then try to find it in the image. No. I don't think we're going to get that lucky. I think this had, what was it saying, 64 megabytes of flash. So, I mean, there's a lot of room in here. This would be tedious without having some kind of automation. I mean, and we could just like dump out all of it over the serial port like this, but that would be very, very slow. Ben is saying the addresses should be documented. Well, that would be cheating, wouldn't it? I mean, let's see if we can find anything in that same source tree that we saw those strings in before. Memmap.h sounds promising. Macrom. That's not the Ethernet Mac, is it? Well, that's not extremely useful. There's probably something at the level of just configuration for it that would tell it where to put the Linux kernel by default. Oh. Where would we find more config files like that? There's probably a lot of that. Can we actually check this out? Something like that, maybe. Oh. Why are those commented out? So I guess we must have been using some kind of mirror of RAM down at 0, or possibly that's the ROM. But this is all saying it looks like SDRAM starts up here at A something or other. More interesting addresses somewhere, maybe. Oh, that's in .config here. But that might be somebody else's change to this. Like, that might not actually match the board that I'm using here. Oh, Ben has a link to some tools for unpacking firmware for similar models. Like, that's useful and it's not useful, because like, while I'm sure it's helpful to have tools for this particular model, I'm also trying to demonstrate techniques that work for a lot of devices. So like, having a website where somebody's already done the work for this particular camera isn't really what I want to be showing right now. So the trouble with this is, if you found the, oh, this might be what I want. No. ISRAM. I mean, we were already looking at most of that, I think. Yeah, I don't know which of these actually correspond with the hardware I have in front of me. Can we dump from here? So if I was really coming up to a platform that I didn't know that much about and trying to figure out what's in RAM, the way I've done this before is to write a script to probe out the memory map by kind of walking through the address space the same way you would be trying to decode it, looking at, like basically treating the address space as a binary tree with the high order bits near the root of the tree and just walking down that tree in kind of a breadth first source search. So is that going to be the same as what's at 0? Yeah, so I think maybe that's just an uncached mirror of SRAM, maybe. Yeah, so if we really cared about getting this data out, I could like grab it just bit by bit using another Python script, perhaps. You could script this to send the md command and grab the resulting text. I thought that would just continue the last command. I guess it does if I don't give the command name. Oh, do we have an endianness issue? Is that why I wasn't finding these earlier? Is this... Oh, I think this is little endian. And this is, as it's written in the file, these are separators. So I think what I actually want to be searching for is something more like... something like that. Ah, it found it. Yay, I just had an endian problem before, probably. That looks right. I think this is the image we're looking for. So 400870. Let's just do a little subtraction here. Is that where we're going to find the beginning of the image? Is that right? So we saw that at... Did I already lose where I had that byte? That was... Whatever. Let's start with 400, 400. That's something that's easy to remember, maybe. So then we want to find... C2DA space 95 F1. Oh, right, and so also we're not going to expect to find all of SpyFlash. We're going to expect to find the kernel image. So we want to find, so the offset we're looking for is OX 150 440 minus the beginning of the kernel, which is 50,000 hex. And let's actually keep that in hex. 100440. And so that seems like what we want. I think we want now that value 100,440 minus, or sorry, we want the RAM address 400,400 minus that. I think that is now the base address of the kernel. Did I still mess that up? It's possible we don't have the whole header for the kernel. It might be that it's reading it at exactly 3 megabytes, but this is a header it's throwing away. Let's take a look at what that looks like. .5D. Yeah, I think it's starting at 3 megabytes and then loading. Oh, that's not what I wanted. Okay. So yeah, this seems unrelated. Then at 3 megabytes it has 5D, which is this line in the kernel header. So, and that makes sense. That's the first 16-byte boundary after this Linux kernel image text. So this is probably a 32-byte long string, and this is some other stuff, like probably size and entry point and stuff like that it would want. Cool. So if we were so motivated, we could start reading the kernel out from here using md commands and get both the kernel and the init rd after it. So effectively all the interesting bits of the firmware, we could just extract it from RAM right here. And this looks so unordered because it's compressed. I think the whole kernel and init rd are LZMA compressed. Okay, so I think that's enough for there. I think maybe the next thing, let's actually get to try to read this directly off the SPI, or off the flash. So I was hoping to do that with the Raspberry Pi. I was also hoping to find a reset, but maybe we just try to do this kind of cowboy style and fight the processor for the SPI bus while we hold this in the bootloader. So we're not actually going to be talking to the SPI from this system on chip, but we'll want, this will actually be running and it'll be driving the line in a particular state. Ben is suggesting to hot air it off, please. Yeah, I could do that too. I don't know which one would make a better demo. Since this is something more people are likely to have access to, hot air is like the correct way to do it. The other thing I was thinking about doing, Ben apparently has killed a system on chip before trying to do what I was about to try. Yeah, I believe it. There are a few other things you could try. There's just cutting the traces temporarily and then bridging them back when you're done. There's the thing that would actually be the cleanest, I think, would be to try to, or soldering iron to flood the sides. Yeah, you can remove these with a regular soldering iron. It's just tricky. There are some products that make that a little bit easier, like this low temperature solder called ChipQuick, that makes it a little bit easier to get all the pins hot. I think the cleanest thing to do would honestly be to figure out how to disable the SPI controller from U-boot. I spent a little bit of time looking at that. Maybe it's worth looking at that a little closer. Because, honestly, the strategy that the LibreBoot folks are supporting with just like clipping onto the chip while it's in the laptop seems likely to work, but also likely to not work. I don't know, there's just a lot of things electrically that are sketchy about this. Like, this whole thing is sketchy. Neither of these are electrically a good idea, but apparently they work for a lot of people. Let's see if we can figure out how to hold the flash controller and reset, with the SPI controller and reset. It'd be really nice to have actual documentation for this chip. This is also something that ventures into less widely applicable territory, though, because if you don't have documentation for your chip's registers, if you can't tell it to please nicely just not access SPI, then you're stuck hot airing off the chip. Yeah, so what are these relative to? I guess we could look at the kernel driver. It would also be really nice to find a hardware reset pin on here. Maybe we go hunting for a reset pin. I saw some test points that might be candidates. It might be worth seeing if any of them, first of all, has 3.3 volts sitting on it when it's idle, and second of all, that I can just tap it low to ground and it doesn't draw much current, but does reset the system. Good question from Ben. If I hold it in U-boot, does it high-Z the pins? I don't think so, because I'm in U-boot right now. Because U-boot can access the SPI. I mean, unless that's high-Z and someone has a pull-up, but I doubt that. Yeah, here's the U-boot. Let's clear that. So this is the closest thing I have is, like, there's no SPI command off or anything like that. So you can see it reading it there. Yeah, if we knew the address of those registers, we could probably turn off the SPI control. Excuse me, turn off the SPI controller. So these are all relative to other stuff. Which repository should I even be looking at here? These are device trees. It's not really what I'm looking for. RA MIPS is apparently the name of this port. I wonder if this is just in mainline Linux. PCI, huh? Sys controller. Do I have a Linux tree on this machine? It would be more convenient to do this locally. So my current plan is to look in the Linux source to try to find how to disable the SPI controller so that we can actually talk to this SPI flash. Otherwise, I might just have to take it off the board. Ben saying, I think reset pin hunting might be easier than register hunting. Well, I think the registers... I mean, I've already spent a little bit of time looking for reset. Yeah, maybe we can spend a little bit more time on that. That's also on the opposite side of the board, which means I've got to flip it. Unplug this thing with the infrared stuff on it. to take these clips off. My serial port connector here is still very fragile. There are some test points on this side that might help us along our way. Let's make sure we can still boot this. Yep, it is going back into the U-boot, so I'll turn that back off. Okay. How close can I get this in? So those two test points right to the left of the CPU are the first things I'm going to check. Other things to look at might be if it looks like there's an RC circuit that could be used for reset timing, but I wouldn't necessarily expect to see that. First, I'm just going to measure voltages. So ground over there. Zero volts, 0 volts, which means it's pretty unlikely either of these is reset. Might need the microscope. I also don't get an immediate reset from either of these buttons, so. Yeah, we could get this into the microscope to look at the passives. A couple of these are obviously decoupling, a couple of them are obviously pull downs for something. There's a leg of a resistor that's 3.3 volts near the CPU, but that could be pretty much anything. Yeah, a couple of these pads over here are reading 1.2 volts, so it could be interesting. That's the resistor over there that might be reset related. Hard to tell. I think the safest thing to do for reset here is to probably try poking things with like a, 1K resistor maybe. Stick one side on ground. And I'm also going to measure the voltage across this. Sorry about the shaking. So I think I want to use this contraption. So I can stick my multimeter probe on a pin that I'm interested in, and I've also got a 1K resistor here that I can attach the other end to ground, and then I'll see if the system resets. And I can watch the voltage on the multimeter. So that's R26. Ground. Maybe this is one of those rare cases where an alligator clip is actually helpful. These will work. The alligator clips could use some organization. Oh, that's a good picture of Tuco. Aww. I love it when his ears go back like that. Yeah. You're so into that little dude. Alright. Antistatic strap on after petting Tuco. Alright. Well, it's something with a pull-up, but it's not reset. I did not get a reset, and the board is still running. Let's see if there's another one over there like that. It's not as likely, but... I'm not seeing a lot that looks like a reset over here. It'd be helpful to have a pinout of this chip, and we might have some idea of where to start looking. Maybe this thing? Any of these? No. It's not seeming too likely. Alright. Well, maybe it's time to pull this off. Hoping to find a simpler way, but maybe pulling it off is actually by far the simplest way to do this. Alright, so let's power this off. Do I have an SO8 adapter handy? I could probably just use clips for the entire thing. I'm going to briefly check to see if I have an SO8 adapter. Go. Maybe they're in this bin. Oh yeah, I've got some of these, which are little SO8 prototyping doodads. That might be the right thing to use for this. This is powered off. That is our serial port. We need to turn this over again. Let's unplug this stuff this time. You know, based on that little paint mark, I would assume that they program these before installing them. Like there's some QA step where they program and test the chips, mark them, and then those go off to assembly. That might just make things faster for them. This doesn't seem to have a dedicated in-circuit programming interface of any sort. The serial will be really slow for that. Alright, well there's the memory. I think we can just pull that off and stick it on here, and then wire it up to our Raspberry. I think this even has roughly 0.1 inch spacing, so we can add headers like that to the stuff we care about. Yeah, something like that. All right. So for this, there are other ways to get it off, but really the most sure way to get it off without damaging things too much is to use a hot air surface mount rework tool. These are not that expensive. You can find one for under $200 that'll last you quite a long time, but it is a little bit more into a little bit further into the specialty tools domain than a lot of these things require. So. Heat the area a little bit since this board is completely cold, and then actually go in for the removal. Chico's hanging out in the kitchen. Oh, this would be fun if I was streaming this in thermal vision too. I'll have to remember to do that next time. Thermal camera can be misleading on the circuit board sometimes with all the shiny surfaces, but Once you learn what you can trust, it's quite a useful tool. This feels like it's getting close. This is about when I start to wonder if I need to have my tool set a little hotter, but it might still just need a little more time. I guess this probably would have been easier if I added some leaded solder to the joints. Lead-free requires a good bit more heat. Yeah, let's bump that tool up a little bit. There are also sometimes other things that you can remove if you're getting out a hot air tool, but you don't really want to take off the flash, possibly because it's BGA. Sometimes there are resistor arrays in between the SPI flash and the system on chip that you could take out. Man, this is really not coming. I blame the lead-free solder. All right, I guess we have to go a little hotter. What is going on with this? This is not usually how long it takes for this to come off. I'm just not used to lead-free boards. Maybe something else is going on. This one doesn't have a thermal pad under it, does it? Maybe it's just cold in the shop today. Actually, it probably does take a lot longer to do this when it's drafty in here. Not budging. I think I might actually try adding some lower temperature solder to it. That's super annoying. Let's put this into the microscope and turn off the O-scope, I think. Give it a little booger of flux on each side to help the solder flow in. So here I'm just trying to mix enough of my leaded solder in there so that it lowers the melting point, which will make it a little easier to hot air in my drafty shop. Oh. Yeah, Milan is saying maybe it's a ground pad, maybe it's glued. I didn't see a ground pad in the data sheet, but it certainly felt like one. And it could be glued. I don't know why they would, but it also kind of felt like that too. But we'll see. It might just be too little heat. Oh, let's do that. Oh, US Water Rockets is saying that they've seen glued parts a lot. Yeah, that sucks. I guess I could see them gluing it if they wanted to keep me from doing exactly this, but why would they care? I mean, usually I see gluing done for manufacturing reasons, like when they populate parts on the backside of the board and then they flip it over. I guess I don't know which side of this board would have been facing up when it was assembled. But if they glued this, maybe that means they glued like all the parts on the backside, if this is the backside. I don't know. That flux still hasn't even really started burning off, so maybe the board is just a really good heat sink, or the shop is cold. This is a good hand warmer, at least. Maybe it's time to use my board preheater, although I was trying to have this use less equipment rather than more. Hey Tuco, I feel you on my leg. Oh, I wonder if there's some kind of coating. No, that's flux. That's flux. It's just very liquid flux. It's still cold. Why is it still cold? Is the whole board just that cold? Do I need more air? Oh, is that the flux bubbling? Maybe I just needed more air to overpower the draftiness in the shop. It looks like the flux bubbling. Oh, and that looks like the solder getting shiny. I hear you, Tuke, but I'm busy. Alright, we're almost good to go. This board is a good heatsink, and I'm like apparently in just too cold of a room for this without the preheater. Maybe next time I just always use the preheater. I'm like, sorry folks, if you want to do surface mount, either buy a preheater or have a warm room. This is definitely the ground plane's fault right now. Come on. There we go. Okay, hopefully I did not damage that, applying so much heat to it. So, I can clean up this board a little bit. Or by clean, I mean make it slightly messier. There we go. Some gook on top of that resistor, but I think it's fine. All right. Now, we have our mount for the board, which is, or for the chip, which is hopefully still fine. Cool. It's barely gonna fit. This is a really wide SO package. This will probably be nicer than trying to just attach it with clips. I'm putting my hand down on wires which are going inside me. I shouldn't allow that to happen. So I should just tack down one of these corners maybe. This soldering iron tip is way too big. Let's change this. Come on, little tip. Oh, I've been meaning to get more of these handles, because apparently that is the way to have the changes be a little less annoying. Alright, soldering iron is warming up again. It's that tip now. This might be a brand new tip. I guess I meant to grab the one that I already used, but this one was sitting right next to it. So as far as other support components, it'd be nice to give this thing a 0.1 microfarad capacitor. We might need to do something with the write protect pin. I forget whether it has a built-in pull-up for that. Since we aren't planning on writing, I guess it doesn't really matter, but that is another thing that could end up mattering. All right. So where do we want the 0.1 capacitor? Just opening up a data sheet. Okay, so power is top right, ground is bottom left. Which is kind of annoying. Let's get a capacitor and some headers. 0.1. This is annoying just because I don't really want to have to run it all the way around, but I don't want to go over the chip because that'll make it harder to get out when that time comes. There's be one benefit to having a custom-made adapter instead of just using something generic like this. That is not soldered very well, but I'm going to solder this other one first so that I have an anchor. This will be the ground. Just running it over so I can get a little bit of local capacitance on this board. Okay, so what do we need to do with write protect here? Write protect input. Write protect is active low, so it should float high normally. Does it have a pull up? I don't actually know. Maybe we give it a pull up. I also kind of don't care because I'm just reading from the chip. So maybe let's just give it some 0.1 headers and move on. Something like that, maybe. crooked. I think we can do better. Let's tack it down on this side first. A little bit floating currently. Let's resolder all those so they're actually durable-ish. I hear you, Tuco. I wonder if he wants to go outside. That one is currently no connects, but I'm using it mechanically. Let's do something similar on the other side. Yeah, I think the combination of lead-free solder and drafty shop is probably what explains it. Hey, Tuco, what do you want, little guy? So something like that. There's at least one too many on there. Anything is a surface mount part. All it needs is to not have holes. It's so simple. That capacitor is going to be a mechanical weak point. Anytime you have mechanical stress directed into a capacitor, it's not really a good idea. But this is all very temporary. And if that capacitor fails short circuit, then my power supply will notice. Okay, got everything broken out. We need to be able to power this chip and read it off from the Raspberry Pi. Done with that for the moment. So for power, I would like to use my bench supply here. Are these clips? Oh no, that's what I was just using. This is my input right now. use some of these. These will be our 3.3 volt supply. Hey, Tuco. Are you gonna jump somewhere tricky, Tuco? Okay, 3.3 volts at 100 milliamps. It is currently off, but I'm just looking up where to connect it all. Oh, let's look that up here. Ground, power. And we want, oh, do we need to connect /hold? That's another pin on here. That is for flow control, I think. Hold input. I'm feeling lazy, so I'm curious if I can just measure whether it has a pull-up. So we kind of want to make sure hold and write protect are high when we're not using them. So either we'll do that with a resistor, or I'm just going to check to see if there's a pull-up with the multimeter. So I'm just going to ground the meter and then measure the idle state of those two lines. So 3.3 volts. No noticeable current draw, which is good. Write protect. Looks like 0 volts. Oh, maybe I'm not measuring this right. Maybe my ground was not actually connected. Okay, 3.3 is good now. Still getting 0 on write protect. Still getting 0 on hold. I guess we do need pull-ups. All right. This is about when it would have been nice to have an adapter that I could actually put into the breadboard. Let's switch this a little bit. I'm going to have the 3.3 volt rail be on this breadboard. Okay, maybe just a whole bunch of clips. I mean, really, a bunch of male to female jumpers would be about right for this. Do I have that? I don't know if I have that handy. All right, let's just do it with what's in this box. else. Okay, DO. Hey Tuco, good job standing on the keyboard. Tuco changes my pinouts. Okay, chip select, pin 1. This will go to CE0 on the Raspberry Pi, I think. Then we have data out. We want master in, slave out on the Raspberry Pi, which is over here. Write protect goes to one of my pull-up resistors. This is not going to be happy with really high speeds, but that's fine. I think we can clock it down pretty easily. So that's everything on the left side of the chip. We've already got VCC. Now hold goes to a pull-up resistor. Clock. Is that going to be over here? S clock. Then one more DI. Well, that is the messiest thing I've used to read an EEPROM in a while, but should get the job done. So we have the memory chip over here in our little surface mount carrier, a bunch of wires, and a Raspberry Pi. These are the pull-up resistors for the pins we aren't using, the write, protect, and hold. So Raspberry Pi, I think, is already running. We can just SSH in there. If we apply power to the memory chip is powered 0.00 amps, which is what we would expect. It is using a tiny amount of power, but way too little for the power supply to measure. So let's go back into the Raspberry Pi. Do we already have one? Just this Minicom, probably. Oh, there's one. Cool. So the tool we want to use for this is that this Flash ROM program. This is the instruction for how to use this to install LibreBoot using the Raspberry Pi. We're doing something pretty similar, but we will need to install this. So there's a Subversion repo and some dependencies. PCI utils. do we need? Is that build essential, not essentials? I always get those two mixed up. No, not Essentia. That'd be like a Final Fantasy VII move. Okay. I think we are done with the O-scope for the moment. So this is a tool which is pretty general purpose, but a lot of people use it to install ROMs on their laptops, apparently. It can read and write several different kinds of flash memory. Yeah. So this is in kilobytes. That's interesting. Yeah, I think we're compatible with this Atmel interface, so like I think this is roughly what we want. AT25 something or other 64. Oh. Cold in the shop. I hear you, Tuco. We're doing one more thing. As much fun as it would be to make some food and work on my rack, we have one more thing to do. I hear you, Tuco. You want some food too? Oh. Hey, Tuco, what do you want? Do the thing. 1955. Ready for the next revision. Wonder when that'll come. USB. I thought I already installed this. Is it the wrong version? Oh, what is this? 1.0-0. Gotcha. Oh, I want the dev package for that. That's what I wanted. Oh, brr. I should probably put this flash ROM back on after we read it. So we were building this program called FlashROM on the Raspberry Pi 3. Well, not the Raspberry Pi 3. I was having problems with the serial port on the Raspberry Pi 3, so I went back to the Raspberry Pi 1. That was what else I had handy. So this FlashROM program will use the built-in SPI on the Raspberry Pi to read the memory from this external chip that we just desoldered. There are a lot of other ways to do this. We could write a little bit of Python code to talk to the SPI interface directly. This program just seems to be pretty much exactly what we already want. This also supports a lot of other interfaces, so you saw it asking for libUSB support. It can talk to various, like I think it can talk to the FTDI adapters, the bus pirate, probably a handful of other things. Yeah, I should get something warm. I'll be right back. Heater is working too. Yes, it just was not apparently quite on. Sometimes the pilot light goes out. Hey, look, it's still compiling. FlashROM.c. I don't have my foot warmer mat. Maybe I should get that and turn it on. There we go. FlashROM. Yay. -P would in this case be Linux SPI. Calibrating delay loop. Wow. Okay, Linux SPI :dev equals. Well, I just want to tab complete that. So that should be chip select 0. Chip name. Oh, I guess it'll by default probe, so we can let it do that. Oh, cool, found WinBond flash W25Q44. So it already knows everything it needs. Great. So read into a file. So let's just call this so it should be reading the whole thing into that DCS933 direct.bin. Power supply is still reporting no current pretty much. I would expect it to be pretty low power reading it, especially reading it this slowly. And one thing the documentation for FlashROM was recommending, which seems like a good deal, is to read it a couple of times and see if they match. That'll at least tell you that any, if you're getting transient errors due to noise or something, that's not happening, because that'll give you different results. It still doesn't tell you for sure that it's correct, but at least you know it's stable. I'm kind of curious how fast this is reading. Oh, there's the clock. Ooh, that is slow. Let's get this on the O-scope. That is what, like 1 megabit? 1 megabit per second. Don't have to worry about our wiring. Can we change the speed easily? The speed might be like a Raspberry Pi thing we have to change. I don't know. It also might be this is hard-coded to always go slowly. That would be a little weird. Let me just, oops. Did not mean to minimize that. I meant to try to get another window so we can see how fast that's going. Oh, well, there's our first one. Okay, let's do that at least one more time. In the meantime, let's copy that over to this machine and take a look at it. Okay, that's the image we just grabbed over SPI. Let's turn off this persistence. Okay. Those are the same. That's a pretty good sign that we read it back correctly. So reading a question from Sean in chat. So since we're reading Flash, does something like QFN specify just the interface format of the chip, so to speak, or does it also specify the dimensions? Oh, that's an interesting question. Generally, QFN just means quad flat with no leads. So I think manufacturers interpret that in different ways. I suspect they're, like, I don't know specifically about QFNs, but the way this usually works is there's a set of standard packages that are standardized by some standards body. I think a lot of the packages are standardized by JEDEC, which is the same body that standardizes memory chips, but I don't know if that applies for QFNs. Okay, so Peter says there are different pitches and pin counts for QFNs. Yeah, I mean, I guess one question is whether the like a QFN48 always has the same pitches and pin counts, or if there are a bunch of different variants. And then Don has a question that I missed. Let me see if I can go back and find that. Oh, so Don is asking about the motives for these streams, whether this is just for my own satisfaction or whether I'm compensated for my efforts. It varies. This particular one is something I'm doing for Sanrio for my day job, but in general, like, I've been doing these streams for a lot of different reasons. I generally try to find some way to support them because it's something I enjoy doing. And just more generally, the thing that I like doing is to just put out content that people can learn from, and kind of on-ramps to get more people interested in this kind of work. So to that end, there are a lot of different ways to accomplish that. I just look for some overall narrative I can tell. So like for this particular project, it seemed to make sense to me to have this narrative of, well, you've got this device, you want to get the firmware off, here's a whole range of different ways that you could do it via this set of interfaces. But then it's also, in this specific case, something that Sanrio wanted, so they had a specific thing they wanted me to do in this case. But yeah, the individual streams tend to vary. Like the one that I've been doing for the cat following robot is just me and my Patreon fans, basically. But a lot of it is stuff that I try to lead with the Patreon, since that's something I hope that maybe at some point after spending more time developing that would actually be able to pay the rent on its own. Or that plus teaching classes here and other places. So it's all a bunch of different things that I hope can fit together. So here's 2 copies. Let's copy them both just for completeness. Oh, okay, so Don is asking if I do contract work. It really depends. I mean, depends a lot on the job and who's asking and if I have time. And right now I feel pretty low on time, but we'll see. Yeah, I mean, you feel free to describe it to me, but it's been something I don't usually have a whole lot of time for lately. But yeah, I think, I don't know, the different ways that I work, it changes a lot, so I don't know, maybe ask me in 6 months and I'll have some different answers. But right now my thing has been kind of doing everything I can to just get content out there and to, to make stuff that I find satisfying, that other people in the community find satisfying, to make things that my Patreon supporters find satisfying. And then specifically right now I'm doing stuff with Sanrio to support creating educational content that they want to get out there and that they want to have on their blog and that kind of thing. Okay, so those are the same, and they're the same as me reading directly from MTD0. Great. So we have just read the same thing directly through HTTP. We started to read it over the serial port, but that would have been really slow to let it finish. And we downloaded it from the website. We tried to get it out by passively sniffing it, which was starting to work, but just had some reliability issues because this logic analyzer couldn't quite keep up. So that would be applicable on either a slower device or a faster logic analyzer, but this time it was having some trouble. Oh, yes. As Ben also says, to provide the much needed cat content for sure. Yeah, definitely got to get the cats out there. Yeah, I'm really looking forward to having the Tuco following camera. I think that'll just be a fun thing for a lot of people, and it'll be fun to describe how to make it. It'll be fun for a lot of people to play with, and it might get more people interested in this kind of, putting things together and taking them apart. So I think we're mostly wrapped up on the stream. I think that's pretty much everything I wanted to do with the firmware. I would like to put this camera back together, so I'm going to do that really quick. I just want to make sure that we didn't totally break it and that I can send it back to my coworkers in one piece. Okay, so I think I can shut down the Raspberry Pi at this point. I think I'm done with that. Okay, and remove some of these terrible wires from everything. Alright, Raspberry Pi is free. Alright, so we will need the hot air again to get this off of our little test board, but then we can just use the regular soldering iron to put it back on the camera. Alright, I'm hoping this comes off a little easier now that it doesn't have lead-free solder all over it. I guess there's some kind of higher level answers to the motivation question too, like why do I want to just like make stuff and share it like this? I guess in some ways things don't really feel real unless they have a way of like propagating. And so, I mean, I could do stuff on my own and that would be fun, but helping other people do it is, I think, maybe a more lasting experience. And then there are a lot of ways to accomplish that. I mean, I like doing things in person, but I have a hard time making that sustainable. So the more I can do kind of via the internet, the more continuously I can keep doing things. Definitely easier to take off that time. No huge ground planes, no lead-free solder. I think this would be a little easier if I cleaned off some of the giant piles of solder on these pads. A little trouble supplying enough heat here. Go, little tip. You can do it. I don't want to change tips right now because I'm lazy. The ground is always harder. Just sucks away all the heat. Okay. So I just wanted those to be flat so I can put the chip down and it doesn't sort of sit at a weird angle. It's hanging out in a sticky pile of flux now. That should be enough of a tack down, and we can do it for real. It's like a little tiny earthquake every time I unspool some more solder. This is not quite sitting perfectly, and I think I might even bend some of the pins a little bit, but this will do. An SO8 is pretty forgiving. I'm having trouble actually getting this soldering iron at the right angle. Alright. That'll do, I think. So, we could watch it boot over the serial port. I'm forgetting which of these is ground. I guess the Raspberry Pi would have been convenient for this. Since this is the last experiment of the evening, I guess we can take our chances with the Prolific adapter. Well, no kernel panic when I plug it in. That's a good sign. So these are our grounds. Oh, you know, I mean, if I was going to put this actually together, I guess I should put the case back on it. But let's watch it boot first. Ground is on the right. Alright, and do we have the ability to attach a minicom to that without the computer completely crashing? I think that might be right. I'm not going to bother with Ethernet, but I do need power. And 5 volts. Alright, it's booting up. That looks like a good sign. We wouldn't have even gotten into U-boot if there was a problem with the SPI flash. I don't know why that's saying Raspberry read. Like, what code did they yank from the Raspberry Pi to get that? Anyway, this looks fine. I think we should put the rest of the case back together. So let's desolder this stuff that I temporarily tacked on here, because this will not fit in the case. How hard is it to get this thing off with this tiny solder tip? I think this is not happening. I might have to switch to the bigger tip just to do this. I don't know. Oh. Yay, okay. Well, that'll be fine. That blob will fit the entirety of that header wasn't. So then let's temporarily take these off. That right one is our old friend, the ground plane. Let's put a little bit of flux pen on there before we... I think cleaning this up slightly before putting the case on would make things easier. Oh, this poor little iron tip. Just can't put enough heat in there. That's fine. Okay, I might switch to the larger tip right before doing that last ground joint, but I think right now I'm just going to put the case together. Two pieces. Oh, and this. So we have 3 screws, 4 screws. So there's this little night vision assembly that goes in the front. This doesn't really have to come out, but I just wanted to take all the electronics out. So that just fits in there. I have 3 tiny screws. Tinier than that. Right now, so we were talking about time management a little earlier, or like specifically how I allocate my projects, and There's some stuff that I really feel like I need to spend more time on, like, been really behind on editing videos, so I kind of want to restructure stuff a little bit so that I can have more time for that. And I'm really excited to get my cat camera finished, so regardless of how things are scheduled, just like at a really high level, I think right now with this particular project, I would love to just spend a bunch of time on it and finish it. And like, nobody's paying me specifically for that, but I think a lot of the people who fund my Patreon would find that project pretty interesting. And then, I mean, everybody likes Tuco, so, I mean, more ways for Tuco to interact with the internet seems like a good thing for everyone. Alright, so that just fits in there. And this will snap on. Oh, actually, there's one screw. One screw in this corner for the circuit board. It's not for heat sinking reasons, I think it's just for alignment reasons. These are not quite the right size screwdriver, but it's in there enough. Alright, snap this on. And almost done. This would normally be done, except we have our trusty serial port, which I'm going to reconnect with a soldering iron. And then we will test it again with everything put together. So these are already in the right order, they just need to go down to the board again. Let's just, while we're here, let's give these all a nice tin. I think that one on the left was not tinned super well. So this is using the solder to conduct heat into the wire and a combination of the heat and the flux to burn off the insulation. So I'm not really using the solder with the intent of having much of it stay on the wire, but I'm using it as a cleaning process. You can see it kind of also helps to scrape away the burn insulation just a little bit with the soldering tip. Doesn't take much. A little bit of depth fail. This is a bit of a deep hole. It doesn't really look it on the microscope, but that ridge is kind of deep. And this one I might even need a thicker soldering tip to work on. Yeah, let's do those left three and then maybe change the tip. Yeah, actually they don't get very warm at all near the base of the tip. That's really handy. All right. Thicker soldering iron tip, which I think I just poked myself with when it was still cold. Braid. There we go. Ow. Touched the still very hot braid with my hand after not paying attention to where I ditched it on the desk. Okay. I think that'll be all right. Let's test it. All right, fully assembled. There's the base, why not? Back to looking like a webcam, kind of. Power and serial. All right, can we boot it again? Looks like yes. Can we talk in both directions? Looks like we have the chat stuck again. I think sometimes you can unstick the chat by going up and editing the previous item. I haven't quite figured out how to have a better workaround. I don't know. This is looking right so far. Cool. I think we're having a good day with this. So we're back in, as always. Looks like it's working. I think we can pack this thing up and call it a day. So several different ways of extracting the firmware this time. And then assembling the camera back in one piece. Cool. Do we have any cat nearby? I think he's been prowling. Any cat we can end the stream with? Hey, Tuco. I don't see him down here. I wonder if he already headed upstairs. Might be time to head upstairs and join him if that's the case. So thanks everyone for joining me. It's been fun. And yeah, hopefully somebody learned something from this. You know, there are always more ways to get firmware out of a device. You know, anything you can use to read the memory pretty much could be used to extract data like this. But hopefully this gave you an idea of a few relatively convenient ways that might work for devices that you're interested in. A few ways that you can use from inside the system if you've made it that far, and a few ways you can use from outside. You know, either kind of sniffing the traffic as it goes back and forth, or taking the chip out entirely. So thanks a lot, everyone. Happy hacking. Until next time, I will see you on the interwebs. And oh, there's Tuco. He came downstairs to join us right in time for the end. Hey, Tuco. Tuco, do you want to play Bolt? Would you like to play any Bolt, little guy? Buddy? Tuco, you're gonna have me tying this cable in knots. Hey Tuco, where's your favorite thing to play with? Do you have bolts around here? That surface mount capacitors. Alright, well I think I should go and hang out with Tuco upstairs some. I'll see you all on the internet next time. Happy hacking.